Hello there, and welcome to Science for Sleep, where curiosity finds a quiet corner and science takes the scenic path towards slumber. Tonight we'll be wandering through a question that is both playful and profound, something that sits at the crossroads of physics, information theory, and the limits of imagination. Does the universe itself have an information limit? Can everything that exists, everything that has ever happened and will happen, be written down in bits like pages of a cosmic book, or stored on some kind of ultimate hard drive woven into reality itself? It might sound like a thought experiment from a science fiction story, but it's a real question asked by real physicists, and the answer has taken us to black holes, to entropy, to quantum mechanics, and to one of the most surprising ideas in modern science, the Bekenstein Bound. Before we start wandering down that road, I'd like to know something simple. Where in the world are you right now, and what time is it for you as you listen? Perhaps it's early morning. Perhaps it's long past midnight. Perhaps you're just lying back after a long day, letting your mind drift. Whatever the case, I'm grateful you're here. And if you find this kind of quiet exploration soothing, it would mean a lot if you gave the video a like or maybe subscribed so more people can find a gentle place to rest and wonder. So let's ease into this question slowly, because it's not one to rush. Imagine just for a moment that everything in your room, every object, every mote of dust, every photon bouncing from the lamp, could be described perfectly by numbers. In fact, you might already know that computers do something a little like this. They describe images with pixels, sound with waves, words with codes of letters. But what if nature itself did something similar? What if the deepest description of the universe was not in the form of solid matter or continuous fields, but in the form of information, tiny packets, bits that add up to all the complexity we see? The leap here is not just that information can describe the world. It's the idea that information is the world. And then comes the stranger thought still, that there might be a ceiling on how much information can exist in any given space. This is where Jacob Beckenstein enters the story. Though we'll take our time before placing his name too firmly. For now, picture a glass of water on your table. Simple enough, clear, perhaps with a few bubbles caught on the side. You could describe its position, its temperature, the arrangement of molecules inside it. And if you were very ambitious, you could try to describe each individual water molecule. It might feel like an endless task. How many possible states could that water take? How much information would you need to capture it all? Intuition says the amount should scale with the volume, the three-dimensional space inside the glass. More space, more molecules, more information. Yet, the shocking twist that Beckenstein discovered is that the information content of a region of space isn't limited by its volume at all, but by the surface area around it. That idea is so counterintuitive that even seasoned scientists had to pause. We'll come back to the reasoning, but imagine the universe whispering to you that boundaries matter more than insides. Think of it like a library that looks massive from the outside, but you discover the number of books you can store depends not on the number of shelves inside, but on the size of the walls. What kind of library works that way? Strangely enough, the universe itself. This matters because it changes how we think about reality. If there's a bound, then the universe has a maximum information density, a limit beyond which you simply can't pack more bits. Like trying to write too many words on a page, the ink would blur, the page would tear, the message would be lost. Except here, the tearing is more cosmic. The system collapses into a black hole. Black holes, as it turns out, are the ultimate information containers, and they play the starring role in this entire story. But before we reach them, it helps to talk about information itself. The word gets thrown around a lot. We use it for news articles, for computer files, for trivia that fills our heads. In physics, though, information has a very precise meaning. It refers to the specific arrangement of a system, the exact state of everything inside. Flip a coin, and there are two possible outcomes. That's one bit of information. Roll a die, 6 outcomes, which takes a little more than 2 bits. Now extend this idea to particles, fields, atoms, galaxies, and you begin to see how the very structure of the universe could be thought of in informational terms. There's a gentle irony here. We often think of the physical world as solid and information as abstract, something stored in books or computers. But in the physics sense, information is as real as mass or energy. In fact, there's a growing idea that the three are all connected, that matter, energy, and information are different ways of describing the same underlying reality. Some researchers even suggest that the entire universe could be described as a kind of computation, not in the sense of a giant laptop in the sky, but in the sense that every interaction, every event, is a processing of information. That may sound abstract, but you already experience a small version of it. Every moment your brain is taking in sensory data, compressing it, storing it, discarding it, building a picture of the world that fits in the limited space of your memory. You never notice every photon, every vibration, every detail. Your mind sets a bound, a limit, and within it, you live your reality. The universe, Bekenstein suggested, might be doing something similar on a cosmic scale. So where does the limit come from? Why can't you just cram infinite information into a finite space? That's where black holes demand our attention. A black hole is the ultimate compression of matter. Take enough mass, push it into a small enough region, and gravity overwhelms everything else. No light escapes, no signal leaves, and whatever falls inside seems lost to the outside world. At least that was the traditional picture. But physicists began to wonder, if information is truly fundamental, can it really be destroyed inside a black hole? That question led to the famous information paradox, a puzzle that has kept scientists debating for decades. Bekenstein's answer, refined by Stephen Hawking and many others, was that information isn't lost. Instead, it's somehow encoded on the surface of the black hole, on the event horizon itself, in units that are tiny but finite. Each little patch of surface can store a certain amount of information, proportional not to its volume, but to its area. That's the Bekenstein Bound. The maximum entropy, or information content of a region of space, is limited by the area of its boundary, measured in Planck-sized bits. Think about that for a moment, and how strange it is. A box of space, no matter how much is inside it, has a maximum information content determined only by the surface that encloses it. The inside is secondary. The boundary is everything. This is the seed of the so-called holographic principle, the idea that our entire three-dimensional reality could be described by information written on a two-dimensional surface somewhere, like a hologram where a flat sheet encodes a 3D image. In the same way, the universe may be a projection of information stored on its boundaries. It's the kind of thought that could keep you awake, unless you let it settle gently. Instead of fighting it, imagine yourself lying on a beach, listening to waves, and knowing that everything you see, the sand, the water, the stars above, might just be a play of information on a cosmic screen. Nothing changes for your senses. The world still feels solid, rich, textured. But underneath, the rules may be very different. Physicists measure this bound in terms of entropy, which is a measure of disorder or uncertainty. The more possible states a system has, the higher its entropy, and the more information it contains. Bekenstein realized that there was a maximum entropy for any system of given energy and size, and if you exceeded it, the system would collapse into a black hole. That collapse, far from being a disaster, was nature's way of enforcing the information limit. You can't cheat the bound. You can't sneak in extra bits. The universe holds the line. You might wonder what this means for us, sitting here, listening, thinking. It means that even though the universe feels boundless, even though stars stretch beyond what we can see, even though the night sky looks infinite, there is a deep sense in which reality is finite. Not small, not cramped, but bounded. Every region of space has a maximum information capacity, a kind of cosmic budget, and within that budget everything we experience must fit. That may sound constraining, but it's also strangely comforting. Just as your brain has a limit to how much it can remember, and just as books have a limit to how many pages they can hold, the universe itself has rules that keep it from becoming an infinite chaos. Those rules are what make order, patterns, and meaning possible. If everything were infinite, if there were no bounds, then perhaps nothing could ever be known at all. And so, as you lie here, listening to the quiet unfolding of ideas, think of yourself as part of this informational tapestry. Every atom in your body, every thought in your mind is part of a bounded system, not less real for being limited, but more real because it is defined, describable, part of a universe that contains everything within gentle but unbreakable edges. When you think about the world around you, it's easy to picture it as made of things, solid objects you can touch and see. A chair, a book, a glass of water, your own hand resting on the blanket. We grow up with the sense that matter is what's truly real, that atoms and particles are the building blocks of everything. But there's a quieter story running underneath, one that whispers in the background of physics. That story is information. Every particle, every atom, every flicker of energy is not just matter, but also a carrier of information, a way the universe records what is happening and how it could change. The idea can sound abstract at first. If you pick up a pebble from the ground, you probably don't think of it as a message. You think of it as stone, with weight and texture, rough edges and cool temperature. Yet in physics, that pebble is also a container of possibilities. Its atoms are arranged in a particular pattern, not in another. Its electrons have certain energy levels, not others. Its molecules vibrate at particular frequencies, not randomly. All of that specificity, all those distinctions, are what we mean when we say the pebble contains information. It's not information in the sense of words on a page, but in the sense of every detail that makes it uniquely itself. To get closer to what this means, it helps to think about coins or dice. If you flip a coin, there are two possible outcomes. Before the coin lands, you don't know which one it will be. When it lands, the result reveals one bit of information. A die has 6 possible outcomes. Rolling it produces a little more than 2 bits of information, because you've reduced 6 possibilities to 1. That's a simple example of how information works. It's the resolution of uncertainty. The more possible states something can take, the more information you need to describe it. Now take that idea and zoom in to the atomic scale. A single atom can have different energy levels, different spin orientations, different ways of being entangled with others. Each of those possibilities is like the face of a die. The atom's actual state is one face out of many, and that choice is information. Multiply this by the atoms in a glass of water, or in your body, or in a star, and you begin to see how rich the informational structure of the universe must be. Every configuration of matter, every pattern of motion, every field fluctuation is a whisper of information being stored, even if we don't write it down in human language. Some physicists have suggested that information may be as fundamental as energy and mass. Energy tells us how much change is possible. Mass tells us how much resistance that change has. Information tells us which particular arrangement exists right now. In a sense, energy and mass describe the capacity for events, while information records the outcome. Without information, everything would blur together into sameness. With it, the universe can distinguish one state from another, one moment from another. It's worth pausing to imagine how deeply this penetrates everyday life. The words you're hearing right now are patterns of air vibrations encoded by my voice. Those vibrations are picked up by your ears, turned into electrical signals and sent to your brain. Each step is an information transfer. The pattern of sound waves is not just noise, it's a structured sequence that carries meaning. And at the molecular level, your neurons are firing in particular ways, their ion channels opening and closing, chemical transmitters being released and absorbed. Every one of those details is information. You're not just hearing the story, you're embodying it in informational patterns across billions of tiny biological switches. Even something as simple as temperature is tied to information. Temperature measures the average motion of particles, but entropy, the quantity linked to disorder, measures how many microstates could exist for the same overall condition. If you have a box of gas, its temperature tells you something broad, but to know the exact arrangement of every particle, you'd need far more information than just temperature. Entropy is a way of counting those possibilities. The higher the entropy, the more possible arrangements and the more information is hidden within. This brings us to a curious paradox. Information is both everywhere and elusive. You can say every particle carries information, but you can't always access it. The pebble in your hand contains details of every atom's position, every electron's spin, every vibration of every bond. But you can't know them all at once. Physics tells us that measuring certain properties disturbs others, thanks to the uncertainty principle. So even though the information exists, it may be beyond your reach. That tension between information existing in principle and our ability to capture it is part of what makes this topic so fascinating. One of the strongest hints that information is woven into the fabric of reality comes from quantum mechanics. In quantum theory, particles are described not by single outcomes but by wave functions, mathematical expressions that encode probabilities. When you measure a particle, you collapse that wave function into a particular outcome, but before that, the particle carries information about all the possibilities. In fact, quantum entanglement, where two particles share a linked state no matter how far apart they are, shows us that information is not always local. Measuring one particle instantly tells you something about its partner, even if they're light years away. It's as though information has a way of leaping across space without regard for distance. If this feels strange, that's because it is. Our brains evolved to handle stones and rivers, not quantum fields. Yet experiments show it's true. And it hints that the universe is less about material stuff and more about informational relationships. Particles don't just have properties. They carry correlations, records of interactions, imprints of histories. Every interaction writes information into the world. When two particles scatter off each other, their momenta change in related ways. Even if you don't measure them, the relation is stored in their states. The universe remembers. This raises a question. If every particle is whispering information, is there an ultimate ledger where all this is recorded? Is the universe like a vast library cataloguing every event? Some scientists lean in that direction, suggesting that the laws of physics are fundamentally about the conservation and flow of information. In many formulations, information can never be destroyed, only transformed. Even if you burn a book, the ink rearranges, the smoke carries molecules, the heat radiates photons. The information is scrambled, but in principle it still exists. The story is harder to read, but not erased. The idea that information is conserved is powerful because it forces us to rethink what happens in extreme situations. Black holes, again, are the test case. When something falls in, where does its information go? If the universe forbids destruction of information, then the black hole must somehow encode it. That's part of what led Bekenstein to propose his bound. The amount of information inside a region is not infinite. It's capped by the surface area. That cap is enforced by the physics of black holes, which represent the maximum information you can pack into a space before collapse. But let's not jump too fast. Staying with the quieter idea for now, think of how ordinary matter speaks. A crystal of salt holds the information of its lattice, ions lined up in repeating patterns. A glass of milk carries the information of proteins folded into intricate shapes. Your fingerprints are informational maps unique to you. Even the cosmic microwave background, the faint afterglow of the Big Bang, is a pattern of temperature variations encoding information about the early universe. Everywhere you look, matter and energy are not just things but messages. This is why some physicists go so far as to say, "it from bit." That phrase, coined by John Wheeler, suggests that physical things emerge from informational choices. The it of matter comes from the bit of information. It's a provocative idea, but not without grounding. Our equations of physics are, at their core, rules about how information can and cannot change. Conservation laws, symmetries, quantum rules, they all describe limits on how information flows. When you start to think this way, the world around you looks different. The tree outside is not only wood and leaves, it is a vast informational structure with DNA encoding instructions, proteins folding into shapes, neurons firing to respond to sunlight. Every breath you take is an information exchange, molecules of oxygen entering your blood, carbon dioxide leaving, each with precise counts and paths. Even your memories are stored as information, distributed across networks of neurons, patterns strengthened or weakened by experience. So the whisper of information in every particle is not just a metaphor, it's a literal description of how reality keeps track of itself. The challenge for us is to learn how to listen, how to decode the whispers, how to understand what the universe is telling us through them. The Bekenstein Bound is one answer, a way of saying the whisper cannot grow endlessly loud. There's a ceiling, a maximum chorus. But before we examine that bound too closely, it helps to fully appreciate the ubiquity of information itself. Imagine shrinking yourself down, smaller and smaller, until you hover near an electron. You can't picture it as a little ball, it's more like a fuzzy cloud, a probability distribution. But within that cloud are details, numbers, parameters. Those are information. Now zoom out to a galaxy. Billions of stars, each with planets, each with magnetic fields and winds. The arrangement of it all is another kind of information. Scale doesn't matter. From the tiniest to the largest, the universe is made of distinctions, and distinctions are information. This view changes how we think about limits, because it suggests that information is not an add-on to matter, but its essence. If matter can't exist without information, then limiting information means limiting how matter can exist. The Bekenstein Bound is not a side rule, but a deep principle, and if information is everywhere, then it makes sense that the bound must be enforced everywhere. The whispers in every particle add up, and at some point the universe says, "That's enough. No more bits can be squeezed in. Beyond this point, collapse." As we drift further into this story, you can think of yourself as part of that whispering sea. Your atoms, your memories, your presence here are all information flowing, conserved, reshaped, recorded. The universe does not forget you. It keeps your details written in the states of particles, in the relations of fields, in the traces of light you reflect. The whisper of information in every particle is the whisper of existence itself, telling the cosmos, "Here I am, and here I remain in some form." When we talk about information, it's easy to imagine it in the familiar form of words, numbers, or images. A message written in ink on paper, a conversation carried through the air in sound waves, a string of digits typed on a screen. These are the kinds of things we encounter every day, and they make it feel natural to associate information with language and symbols. But physics asks us to widen the scope dramatically, to look at information not just as something humans use, but as something nature itself cannot avoid producing. The question then becomes, what exactly counts as information when we strip away our human habits of writing and speaking? Consider a simple example. If you look at a book, you see text arranged in patterns. The words carry meaning for you because you can read them. But to the paper, to the ink, to the atoms, there is no English or French or Chinese. There are only molecules arranged in specific ways. Information in physics is not about meaning. It's about distinction. The fact that the ink is here and not there, the fact that one page has this pattern and another has that pattern, those are distinctions, and distinctions are the raw currency of information. Whether anyone reads them or not is irrelevant. This helps us move from words to atoms. An atom itself is information. The number of protons it has, the number of neutrons, the arrangement of its electrons, the specific quantum states they occupy. All of these are differences, and differences count. If hydrogen has one proton while helium has two, that's information. If one electron is in a ground state while another is excited, that's information. Even the spin of a single particle, up or down relative to a chosen axis, is a binary piece of information, much like a bit in a computer. That parallel is not accidental. In computer science, we store information in bits, zeros and ones. They're arbitrary, chosen symbols, but what matters is that they can be distinguished. 0 is not 1. A magnetic domain pointing north is not pointing south. A switch open is not closed. These are distinctions we can manipulate to encode information. Nature does something similar at the fundamental level. The electron's spin, up or down, a photon's polarization, horizontal or vertical, a nucleus aligned or not aligned with a field. These become the universe's bits. They don't need to mean anything in human terms. Their existence as distinct states is enough. So what counts as information? The short answer is any specification of a state out of many possibilities. If a system could be in multiple configurations and it happens to be in one, then the choice of that one contains information. If you toss a coin, there are 2 possibilities. The result gives 1 bit of information. If you shuffle a deck of cards, there are 52 factorial possibilities, an astronomical number. The actual order you produce contains far more information, because it picks out one sequence from a vast space of alternatives. In physics, this is closely tied to entropy. Entropy, at its core, measures the number of microstates consistent with a given macrostate. A macrostate is what you can observe on a large scale, say, the temperature and pressure of a gas. But many microstates of molecules could realize that same temperature and pressure. Entropy tells you how many. The more microstates, the higher the entropy. The higher the entropy, the more information you would need to describe the system exactly. This brings us to an important point. Not all information is useful to us. Much of it is hidden in details we never access. If you have a hot cup of coffee, you know its temperature and volume. But the exact position and velocity of every molecule is beyond your reach. That information exists, but you don't hold it. Thermodynamics simplifies by giving you averages, because in practice you don't need the rest. But from the universe's point of view, those details are still real. They still count. Imagine holding 2 glasses of water. To you they might look identical. Both are transparent, both have the same volume, both at the same temperature. But at the molecular level, they are different. The molecules are not in the same places, their velocities are not matched. Each glass has a unique microstate. To specify one glass completely, you would need to write down an enormous amount of information, more than any notebook could hold. It's there whether you look or not. This is where Beckenstein's insight becomes so startling. If you try to imagine writing down the total information of a region of space, you might assume the number of bit scales with the volume. More space means more molecules, more states, more possibilities. But what he found is that the bound scales with surface area. That means the universe limits not by how much space is inside, but by how big the boundary is. Information is written not in the bulk, but on the edges. Before diving further into that, it's worth asking why physicists care so much about counting information in the first place. One reason is that physics at its heart is about predicting. If you know the state of a system now, you can try to say what it will be later. To do that, you need information about its present state. The better your information, the better your prediction. But if there's a maximum to how much information you can have about a region, then there's a fundamental limit to how precise your predictions can ever be. It's not about our instruments, it's about the rules of nature. To bring this back down to something familiar, think of digital photos. A photo can be stored at different resolutions. The higher the resolution, the more pixels, the more bits of information. At some point, though, adding more pixels doesn't give you more detail, because the image itself has a finite resolution. The physical scene only contained so much information in the light that reached the camera. Beyond that, extra pixels just duplicate. In a similar way, the universe seems to say that there's a maximum resolution to reality itself. You can't store infinite bits in a finite space. The surface sets the limit. This raises another question. Is all information physical? Some argue yes. Every piece of information must be embodied in a physical system, a mark on paper, a state of a particle, a configuration of neurons. Without a physical substrate, information is only an abstraction. This idea, sometimes summarized as information is physical, underpins modern thinking in physics. Even the act of erasing information has a cost. Landauer's principle tells us that erasing one bit of information requires a minimum energy cost of kT-ln2, where K is Boltzmann's constant and T is temperature. That connects information theory directly to thermodynamics. Destroying a file on your computer is not free. It releases heat, however small, because erasing information increases entropy. From this perspective, words and atoms are not separate categories. Words are information encoded in ink or pixels. Atoms are information encoded in quantum states. Both follow the same rules. The leap that Beckenstein and others made is to realize that the rules extend even to space-time itself. The geometry of the universe, the curvature of space, the event horizons of black holes, all can be described in informational terms. That's where the bound comes in. Space-time has an informational capacity, a maximum number of bits per surface area. If you let your mind drift on this idea, it changes how you think about reality. Imagine you're looking at a night sky. The stars seem endless, the space between them vast. But in every patch of that sky, there's only so much information. It's not infinite. The photons reaching your eyes carry bits, and there's a ceiling to how many bits can exist in that patch of sky. The universe is not a bottomless well of distinctions. It's finite, bounded, though the bounds are so large that to us they feel limitless. You might wonder if this has anything to do with meaning. After all, when we think of information in human life, we care about messages, stories, knowledge. Physics doesn't touch meaning directly. To physics, information is simply states and distinctions. But meaning emerges from patterns in information, from correlations, from structures we interpret. The same physical substrate could carry different meanings depending on context. A string of bits might be an image, a song, or nonsense depending on how you decode it. But the physical information is there regardless. This duality, information as raw state versus information as interpreted meaning, mirrors the way we interact with the world. To physics, your brain firing is information. To you, it's a thought, a memory, a story. Both views are valid. One is microscopic, the other macroscopic. The Bekenstein Bound speaks to the first view. It doesn't tell us what the information means. It only tells us how much of it can be there. Meaning is layered on top by minds like ours. Another subtlety is that not all distinctions are equally accessible. Quantum mechanics shows that some information is fundamentally hidden. You can't simultaneously know a particle's position and momentum with arbitrary precision. That's Heisenberg's uncertainty principle. So while the particle carries information, you can't retrieve it all at once. This makes the concept of an information bound even more striking. Not only is there a maximum, but much of what exists is beyond our grasp. We live in a sea of whispers we can only partially hear. It's tempting to ask whether the universe itself processes information. If particles carry it, if fields exchange it, if entropy counts it, does that make the cosmos a kind of computer? Some researchers embrace this analogy, suggesting that physical processes are computations carried out on the state of the universe. Every interaction is like a logical operation, updating the cosmic memory. Whether or not you accept the metaphor, the practical consequence is that the laws of physics can be seen as constraints on how information flows, energy is conserved, momentum is conserved, and perhaps most deeply, information is conserved. This conservation is what makes the Bekenstein Bound so critical. If information cannot be destroyed, then it must always have a home. The bound tells us how large that home can be in a given region. Cross the threshold, and the system transforms into a black hole, which encodes the information on its surface. In this way, black holes are not information graveyards, but maximal information stores. They embody the principle that information is physical and bounded. As you listen, it may help to think of your own surroundings. Every detail in your room, from the folds of fabric on your pillow to the flicker of light on the wall, is an arrangement of atoms, and therefore a configuration of information. Your senses absorb only a fraction of it. Your brain filters even more. Yet the information exists, woven into the air, the objects, the electromagnetic fields around you. What counts as information is everything that distinguishes one moment from another, one state from another. It is the reason why time feels like a sequence instead of a blur. It is the reason why you can remember yesterday and anticipate tomorrow. In the quiet of this moment, you're surrounded by a universe whispering not just matter and energy, but bits and distinctions. Every atom carries its record. Every photon bears its polarization. Every interaction writes something new into the cosmic ledger. Information is not optional. It is the texture of reality itself, the thread that stitches events together. From words to atoms, everything counts. When you first look at the night sky, the thought of limits feels absurd. Stars scatter across the black, galaxies drift at unimaginable distances, and space seems to stretch without end. From our perspective, the cosmos is the very definition of boundlessness. You can always imagine going farther, always picture more stars just beyond the horizon. That sense of infinity has been part of human imagination for as long as people have tilted their heads upward. Yet, here in the heart of modern physics, we come face to face with a different idea. The possibility that the universe has strict mathematical limits on something as fundamental as information. It's a strange and even unsettling notion. How can there be boundaries in something that feels endless? Part of the confusion comes from how we think about infinity. For many of us, infinity is not just a number, but a feeling, a sense of vastness. You can always add one more to any number, so why not keep going forever? You can always picture more stars beyond the visible ones, so why not believe in infinite space? Infinity feels like freedom, an absence of walls, and yet, in physics, infinity is often a red flag. It usually signals that a theory is broken down. If your equation spits out infinity, it doesn't mean the world is infinite. It means you've asked a question the equation isn't designed to answer. That's where the idea of limits enters. Limits in physics are not always barriers you run into like a wall. They're ceilings built into the rules themselves. You don't experience them as hard stops, but as principles you can't get around. The speed of light is one of the most famous examples. For centuries, people assumed speed was unlimited. You could move faster and faster without bound. Then Einstein came along and showed that there is a cosmic speed limit built into the structure of space-time. Nothing with mass can go faster than light. It wasn't what people expected, but experiments confirmed it. The Bekenstein Bound is a similar kind of limit. It says that no matter how big or small a region of space is, there is a maximum amount of information it can contain. Beyond that, the system doesn't just keep holding more bits, it collapses into a black hole. The rule is not obvious. Nothing in your daily life suggests that information has a ceiling. You can always write more words, add more detail, record more numbers, but nature is stricter. The cosmos doesn't allow infinite information density. Why is this so strange? Because the universe otherwise feels infinite. Space seems to go on forever. Time seems to stretch indefinitely in both directions. Even the number of particles can seem countless. The very word cosmos conjures images of endlessness. And here we are being told that information, the very thing that describes all those particles and all that space, has a maximum. It feels contradictory, like being told the ocean is infinite but the water molecules are capped. Yet that's exactly the kind of paradox that physics forces us to confront. Think about it this way. Suppose you had a box, 1 meter on each side. You fill it with particles, arranging them in as many different ways as you can imagine. Each arrangement is a different microstate, and the total number of microstates is proportional to the amount of information in the box. You might think the number just keeps climbing as you add energy, as you pack more particles, as you shuffle them into finer distinctions. But eventually you hit a point where adding more energy doesn't just increase the information. Instead, the box collapses under its own gravity and becomes a black hole. At that moment, the information is no longer stored in the volume, it's stored on the surface. The limit has been reached. This is what makes the idea strange. It tells us that infinity is not the ultimate story. The cosmos plays by rules that enforce finiteness even in the midst of apparent endlessness. That doesn't mean the universe itself isn't spatially infinite, it still might be. Cosmologists debate whether the cosmos wraps around or extends forever. But whether space is infinite or not, any finite region within it has an information limit, and that limit is proportional not to its volume, but to its surface area. The surface holds the keys. Another way to see the strangeness is through analogy. Imagine you're reading a massive novel, thousands of pages, tiny print packed with detail. You'd expect the total information of the story to depend on the number of pages, on the volume of words inside. But now imagine being told that the book's information capacity is fixed not by the number of pages, but by the size of its cover. No matter how many pages you try to add, the cover size sets the maximum. Beyond that, the book would collapse into something else entirely. That's the kind of counterintuitive twist the Bekenstein Bound gives us. It also challenges our intuition about complexity. We often assume that more volume means more complexity is possible. A larger room can hold more people. A larger field can host more animals. A larger computer memory can store more files. But in physics, at least when it comes to ultimate limits, the surface is what matters. The larger the boundary, the more information inside. Double the boundary, double the maximum information. The inside is secondary, the edges rule. Why edges? That question takes us to black holes. When matter falls into a black hole, the information about it seems to vanish. But Hawking and Beckenstein showed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. That result stunned physicists. It implied that everything about the black hole's interior is somehow encoded on its surface. The information isn't lost, it's written on the boundary. That discovery didn't just redefine black holes, it suggested that the entire universe might work that way. The idea is unsettling because it shifts our mental map of reality. We're used to thinking of the bulk, the inside, as what's real. The surface is just the boundary, the container. But the bound suggests the opposite. The surface carries the ultimate count. It's as if reality itself were holographic, as if the three-dimensional world is a projection of two-dimensional information on its boundary. That doesn't make your experience any less three-dimensional. It just tells us that the deeper bookkeeping of the universe happens at the edges. What makes this especially strange is that it suggests a profound economy in the cosmos. Nature doesn't allow infinite complexity in finite regions. It enforces a budget. You might not notice it in daily life because the bounds are so astronomically large. The information capacity of a single cubic meter of space is unimaginably greater than anything you could practically use. But in principle, the limit is there. Just like no one approaches the speed of light in daily life, but the limit still holds. No one reaches the Bekenstein bound in daily life, but the ceiling still exists. The idea of limits also has philosophical weight. We often imagine knowledge itself as unbounded. There's always more to learn, more to record, more to discover. But if the universe enforces an informational ceiling, then there may be things that cannot be known in principle, not just in practice. The cosmos may hide details simply because there isn't room for them. That doesn't mean mystery disappears. If anything, it makes mystery a structural feature of the universe. There will always be questions that no amount of effort can answer fully, because the information isn't there to be accessed. At first, this can sound discouraging. We like to think of human curiosity as limitless, able to uncover everything given enough time. But in another sense, limits make things meaningful. A game without rules isn't really a game. A story without an ending isn't really a story. The universe's limits give structure to its vastness. They make it possible for knowledge to exist, for predictions to be meaningful, for events to unfold in an ordered way. Without limits, everything would dissolve into undifferentiated infinity, and perhaps nothing coherent could exist at all. To appreciate how deep this runs, think about digital storage again. A computer hard drive has a maximum capacity. You can fill it with photos, songs, texts, and videos, but eventually the space runs out. That limitation shapes how you use it. You compress files, delete old ones, make choices. The cosmos may be similar on a fundamental level. It doesn't allow infinite storage in finite regions. It demands efficiency, compression, boundaries, and yet, the sheer scale of the limit is so vast that it hardly intrudes on our lives. The information capacity of even a small region of space is far beyond anything we can practically fill. The bound is not a daily constraint. It's a principle revealed at extremes, near black holes, at the Planck scale, in the deep structures of space-time. To us, the universe feels infinite because the bounds are so high. It's only when we push against the edges of theory that we glimpse them. The strangeness of limits in an infinite cosmos also reshapes how we think about infinity itself. Perhaps infinity is not something the universe contains, but something we project. We see the vastness and call it infinite because it feels unending. But the mathematics of physics tells us that within that vastness there are still ceilings, still maximums, still rules that prevent true infinity from being realized in finite pockets. Infinity is an idea, not a physical reality. The universe may stretch without end, but each piece of it is finite in its informational content. As you reflect on this, lying back and listening, you might sense a kind of balance in it. The cosmos is not stingy. It allows for extraordinary richness, unfathomable complexity, layers of detail beyond imagination. But it is not wasteful either. It does not scatter infinite distinctions into every corner. It enforces a quiet discipline, a structure that makes the whole coherent. That's what makes the idea of limits in an infinite cosmos so strange. It tells us that reality is both endless and bounded at once. When limits are proposed in science, they don't usually appear out of nowhere. They arrive in the hands of people who are willing to ask questions that others think are unnecessary or even impossible. That was true for Jacob Beckenstein, a young physicist in the early 1970s who found himself staring at black holes not with fear, but with curiosity. The black hole had long been considered an endpoint, a place where matter collapsed so completely that nothing, not even light, could escape. Many thought of them as cosmic sinkholes, emptying the universe of information forever. But Beckenstein, still a graduate student at the time, had the audacity to ask whether that picture was really complete. At the heart of his question was entropy, the measure of disorder in information content. In ordinary thermodynamics, entropy always increases. Burn a log in a fireplace, and the neat arrangement of molecules in the wood becomes scattered smoke and ash. The overall disorder rises. That's the second law of thermodynamics, one of the most solid rules in physics. But what happens if you throw that log into a black hole? From the outside you would no longer see the smoke, the ash, or even the log itself. Everything vanishes behind the event horizon. If entropy must always increase, where does it go? Does the universe simply lose track of it forever? To many at the time, that was the end of the discussion. Black holes swallowed everything, including information. They were the ultimate erasers of the cosmic chalkboard. But Beckenstein wasn't satisfied with that answer. He believed the second law was too fundamental to be violated, even by black holes. If entropy always increases, then something must account for what disappears into the darkness. That line of thought led him to propose that black holes themselves have entropy, and that their entropy is proportional not to their volume, but to the area of their event horizon. It was a bold claim. Black holes were supposed to be simple objects described only by their mass, charge, and spin. That was the so-called no-hair theorem. Black holes have no other features, no hair of complexity. Bekenstein was suggesting otherwise, that they carry a hidden property, entropy, that reflects the information swallowed, and even stranger, that the entropy scales with area, not volume. He didn't have a complete proof, but he had enough reasoning to publish the idea, and it sparked immediate debate. At first, many physicists resisted. The idea seemed speculative, maybe even reckless. Entropy was tied to microscopic degrees of freedom. How could a black hole, with no internal complexity that anyone could see, have entropy at all? But Beckenstein held his ground. He argued that if black holes destroyed entropy, then the second law would be violated, and that simply couldn't be right. The universe, in his view, kept better records than that. What made his proposal especially radical was the suggestion of a bound. If black holes have entropy, and if that entropy scales with surface area, then the maximum entropy of any region of space must also scale with surface area. You can't pack more information inside than would fit on the surface that encloses it. If you try, the region collapses into a black hole, and the bound is enforced. That realization was the birth of what we now call the Bekenstein Bound. To appreciate how groundbreaking this was, it helps to recall how scientists thought about space before. If you fill a box with gas, the number of microstates, and thus the entropy, seems to scale with the volume of the box. Double the volume, double the capacity for states. That's the intuition we all share. But Beckenstein was saying the cosmos doesn't work that way. The ultimate limit is not about volume, but about area. It's as if the universe is two-dimensional at its most fundamental level, with the third dimension being emergent, like a projection. Bekenstein's idea didn't exist in isolation. Around the same time, Stephen Hawking was working on the physics of black holes. At first, Hawking argued that black holes could not radiate, that they were truly dark. But then, through a surprising calculation, he discovered that black holes do emit radiation, now called Hawking radiation. That radiation has a temperature, and with temperature comes entropy. Hawking's work confirmed what Beckenstein had proposed. Black holes really do have entropy, and it is indeed proportional to the area of the horizon. Beckenstein, once a young outsider, had been vindicated. What emerged from these discussions was a deeper understanding of the connection between gravity, thermodynamics, and information. Beckenstein had forced physics to confront a truth that was hiding in plain sight. Information cannot be destroyed, not even by black holes. If the log you throw into a black hole carried information, that information must be encoded somehow, somewhere. The event horizon's area is the key. Each tiny patch of the horizon corresponds to a small amount of entropy, a few bits of information. Add them up, and you get the total entropy of the black hole. The numbers themselves are staggering. A black hole with the mass of the Sun has an entropy of about 1077 bits. That's a 1 followed by 77 zeros. Compare that to the entropy of the Sun itself, which is about 1057 bits. The black hole version is 20 orders of magnitude higher. That means the black hole is a far more efficient information storage device than ordinary matter. In fact, it's the ultimate storage device. Once matter collapses into a black hole, the information is maximized, written across the horizon. No system can pack more information into the same space. That's why black holes embody the Bekenstein Bound. They're nature's way of showing the ceiling. Bekenstein himself was a careful thinker, not prone to exaggeration. He approached the idea with humility, acknowledging that he didn't have all the answers. But he had the courage to follow the logic where it led, even when it contradicted accepted wisdom. That's part of what makes his contribution so memorable. Science often advances when someone refuses to accept a paradox as final. Instead, they dig until they find a resolution. Bekenstein's resolution was that black holes don't erase information. They force us to redefine how it's stored. As you listen to this, it may be worth reflecting on the personality required for such a discovery. Imagine being a graduate student challenging the established view of black holes, going against giants in the field. It takes both confidence and curiosity. Confidence to publish the idea, and curiosity to keep exploring it even when others doubt you. Bekenstein had both, and the result is a principle that reshaped our understanding of physics. The birth of the bound also opened doors to entirely new theories. If entropy scales with area, not volume, then perhaps the universe itself is holographic. Perhaps our three-dimensional world is a projection of information written on a two-dimensional boundary. That's the holographic principle, an idea that grew directly from Bekenstein's work. What started as a student's attempt to save the second law of thermodynamics blossomed into one of the most profound insights in modern physics. But the bound is not just about black holes, it applies to every region of space. Imagine enclosing a region with a surface. The amount of information inside cannot exceed the area of that surface, measured in Planck units. Planck units are unimaginably small, 1035 meters. Each tiny square of area can store a few bits. Add them together, and you have the maximum information for the region. That's the bound. It's not just a curiosity, it's a universal rule. The implications are still unfolding. If information is bounded, then so is complexity. No matter how intricate a system becomes, no matter how many particles you pack inside, there's a maximum. The cosmos won't allow infinite complexity in finite regions. That realization forces us to rethink ideas of infinity, chaos, and even computation. If the universe is a computer, it has limits on its memory and processing. Those limits are not arbitrary. They are written into the geometry of space itself. Looking back, it's striking how such a profound idea began with a simple question. What happens to entropy when matter falls into a black hole? From that question came a bound that ties together gravity, thermodynamics, quantum theory, and information. Bekenstein's insight was not just about black holes, it was about the universe itself, about the way reality enforces its own bookkeeping. Information cannot be destroyed, but it cannot be infinite either. It is bounded, disciplined, and woven into the surfaces that shape space. In the quiet of this reflection, we see the birth of a bound not just as a technical result, but as a turning point. A young physicist asked a question, refused to let go of it, and in doing so uncovered a principle that now guides how we think about reality. From that moment onward, the universe was no longer just stars and galaxies. It was also bits and bounds, surfaces and limits, information written into the very fabric of space-time. When Jacob Beckenstein first suggested that black holes carry entropy, it shifted them from being silent voids to something more like keepers of records. That image is useful because it moves us away from the old view of black holes as pure destroyers and toward a view where they act more like guardians of information. The metaphor that grew from this is that black holes are cosmic librarians. They may not let you borrow back what you put in, but they never discard it either. They hold on to the information, cataloguing it in a way we don't yet fully understand, storing the details of everything that falls inside. To picture this, imagine a library that looks empty from the outside. No windows, no visible shelves, no noise of pages turning. You throw a book into a chute, and the book vanishes. From your perspective, the book is gone forever, but behind the sealed doors, the library has recorded it. The information is filed away, not lost, but inaccessible. That's how black holes behave. You toss matter in, and it seems to disappear. But Beckenstein and Hawking showed that the information isn't erased. It's encoded in the horizon itself, written into the very geometry of the boundary. The encoding isn't like letters in ink or files on a computer. It's subtle, woven into the physics of the horizon. Each bit of information corresponds to a tiny patch of surface area, on the scale of the Planck length. You can imagine the event horizon as a tapestry of unimaginable density, each thread holding a sliver of information. The more mass you add to the black hole, the larger its horizon grows, the more surface area it has, and the more information it can store. That's the bookkeeping system of the universe, meticulous and consistent. This perspective changes how we think about black holes. Instead of erasers, they're archivists. Instead of destroying data, they're reorganizing it. When a star collapses into a black hole, its matter is compressed beyond recognition. From the outside, all you see is mass, charge, and spin. The details of the star's internal structure, the distribution of atoms, the fusion reactions, the patterns of convection, are gone to you. But according to the Bound, they're not gone from the universe. They're just hidden, locked into the surface code of the horizon. The library keeps the book, even if you can't check it out again. What makes this image even more striking is the role of Hawking radiation. When Hawking showed that black holes emit radiation, he revealed that they're not eternal. They evaporate very slowly by radiating particles. Over vast timescales, black holes shrink and eventually disappear. This creates what's called the information paradox. If the black hole evaporates, what happens to the information stored on its horizon? If it simply vanishes, then information is destroyed, violating the principle of conservation. If it somehow escapes with the radiation, then the black hole isn't just a passive librarian, it's an active one, releasing the information in scrambled form. The paradox has kept physicists busy for decades. Some believe the radiation does carry the information, hidden in correlations between emitted particles. Others propose that the information remains in remnants, or that space-time itself ensures its preservation through holography. Whatever the solution, the paradox underlines how seriously physics takes the idea that information cannot be lost. The library may look like it burns down, but the records must survive somehow, somewhere. It's worth pausing here to reflect on why physicists insist so strongly that information can't be destroyed. After all, in daily life it seems like it can. Burn a photograph and the image is gone. Delete a file and the text disappears. But at the fundamental level, the laws of physics are reversible. Every process has, in principle, enough information to be reconstructed backward. If you knew the exact positions and velocities of every particle in the smoke and ash of that burned photograph, you could, in theory, reassemble the photo. In practice, it's impossible because the details are scattered beyond retrieval, but in principle, nothing is truly lost. That's why black holes pose such a challenge. If they erase information absolutely, then they break one of the deepest symmetries of physics. So black holes stand as cosmic test cases. They're the most extreme conditions we know, where gravity is overwhelming, where space-time itself bends into a trap. If information can survive there, then perhaps it really is indestructible. The library image captures this tension. On the one hand, black holes hide information so thoroughly that to us it's as if it's gone. On the other hand, theory tells us the universe won't let it vanish. The information is catalogued, held, preserved in the horizon's tapestry. Another way to think about it is through compression. A black hole is like the ultimate file compressor. You feed in a massive amount of data, the states of particles, the structure of stars, the complexity of galaxies, and the black hole reduces it all to surface information. The details are compressed into the minimum possible form, a code written on the horizon. You can't decompress it without the key, but the data is there, stored in the most compact way allowed by the laws of physics. That's why black holes saturate the Bekenstein Bound. They're the densest libraries possible. It's natural to wonder what kind of language this library uses. In human libraries, information is written in alphabets, numbers, symbols. In computers, it's binary code, ones and zeros. For black holes, the language is geometric, quantum, woven into the shape of space-time. Each Planck-sized patch of area corresponds to a few bits. The entire surface is the text, written in a script we're only beginning to decipher. Some theories suggest it's connected to quantum entanglement, that the links between particles are the letters of the code. Others suggest deeper principles of holography, where the surface encodes a lower dimensional representation of the interior. Whatever the truth, the library has its own alphabet, precise and unyielding. This metaphor of cosmic librarianship also changes the emotional tone of black holes. They're no longer just monsters devouring stars, they're keepers of memory. The collapse of a star into a black hole doesn't mean its story is erased. It means its story is stored in a different form, inaccessible to us, but not gone from reality. That's a gentler picture, one that preserves continuity rather than annihilation. It suggests the cosmos is more careful than we might think, more protective of its records. Consider too the scale of this storage. A black hole with a horizon a few kilometers across can store more information than all the books ever written by humans, more than all the data on Earth computers, more than the neural connections in all human brains combined. The scale dwarfs our imagination. The cosmos doesn't just keep records, it keeps them in bulk, in libraries so vast that our entire history is a footnote on a single shelf. What makes this all the more fascinating is that the library is sealed. You can't enter and read the shelves. Once matter crosses the horizon, no signal can return. The information is inaccessible from our perspective. That makes black holes both reassuring and frustrating. Reassuring because the information isn't lost, frustrating because it's hidden beyond recovery. The universe keeps its own archives, but doesn't let us browse them. It's as if the cosmic librarian is strict about lending policies. The records are safe, but you can't check them out. This tension between preservation and inaccessibility continues to drive research. Physicists ask whether the information might someday be retrieved in subtle ways, perhaps in correlations of Hawking radiation, perhaps in quantum gravitational effects at the horizon. The answers are not yet clear, but the very fact that we ask these questions shows how deeply the librarian metaphor has taken hold. Black holes are no longer seen as destroyers, they are custodians, and the details of their filing system are one of the greatest mysteries left to solve. As you think about this, it may help to bring it back to your own sense of memory. Imagine all the experiences you've ever had, every moment, every detail, stored somewhere, even the ones you've forgotten. The library of your mind holds far more than you can consciously access. Black holes are similar on a cosmic scale. They hold the records even if no one can recall them. The universe is a keeper of memory, unwilling to let information slip into nothingness. When we speak about entropy, it's tempting to treat it as an abstract number, something tucked away in physics textbooks, a term used by specialists to describe the behaviour of gases and engines. But entropy is not confined to laboratories or equations. It's everywhere, woven into every process you've ever seen. Every melting ice cube, every flickering flame, every gust of wind is quietly following the law of entropy. It's the rule that says disorder tends to grow, that the universe prefers to move from tidy arrangements toward messier ones. Yet beneath that apparent march toward chaos, entropy is also a storyteller. It doesn't just measure disorder, it records the history of how systems change, a tally of the possibilities that have been explored and the ones still available. To begin to sense what entropy really is, it helps to go back to something ordinary. Picture a deck of cards. If the cards are neatly ordered by suit and rank, that's a low entropy state. Only one arrangement fits that description. But shuffle the deck, and the number of possible configurations skyrockets. Now there are more ways to be disordered than ordered. Each shuffle takes the deck into one of those countless arrangements, and the odds of returning to the original neat order are vanishingly small. That's entropy at work. The more possible microstates a system can occupy, the higher its entropy. This way of thinking makes entropy less mysterious. It's not a vague force pushing toward chaos. It's a way of counting. High entropy means many possible arrangements are consistent with the big picture view of the system. Low entropy means only a few are. A cup of hot coffee cooling in a room is a perfect example. The high energy arrangement of molecules in the coffee could, in principle, all remain bunched together, but it's overwhelmingly more likely that they spread their energy into the air, raising the entropy of the combined system. The story the coffee tells is one of diffusion, of order giving way to the more probable disorder. Now bring this back to black holes and information. When Jacob Bekenstein argued that black holes must have entropy, he was insisting that they too tell a story. Throw a log into a fireplace, and the entropy increases in a way you can trace. The smoke, the ash, the heat. Throw a log into a black hole, and at first glance the story ends. Nothing comes back out. But Beckenstein realized that if entropy always rises, then the black hole itself must be keeping count. Its surface area increases when you add mass, and that increase is a measure of entropy. The disorder, the story, is not lost. It's just shifted into a new form. The remarkable thing is how vast that entropy is. For a black hole, the entropy is not proportional to its volume, but to its area. That means its ability to tell a story, to keep a record of all that has fallen in, is set by the size of its horizon. The larger the horizon, the more information it can store. That's why we sometimes say black holes are the ultimate record keepers. They may not reveal their pages to us, but they do not stop writing. Every bit of matter or energy that crosses the horizon is another line in the record, another increase in entropy. This ties entropy to time in an intimate way. One of the reasons time seems to flow in one direction, from past to future, is because entropy increases. A glass shatters on the floor and the pieces scatter. You never see the reverse, pieces assembling themselves into a glass. The forward arrow of time is defined by entropy's rise. It's not that the laws of physics forbid reversal. At the microscopic level, the equations work in both directions. But the number of disordered states is so much larger than the number of ordered ones that the system almost always evolves toward disorder. Entropy is the narrator of time's arrow. When you fold that into the story of black holes, the picture becomes even richer. A black hole's entropy is a measure of all the possible internal states it could have, consistent with its external appearance. From the outside, you only see mass, charge, and spin. But the entropy counts the hidden microstates, the vast library of possibilities concealed behind the horizon. Each configuration is like another version of the story, invisible to us, but written into the fabric of space-time itself. What makes entropy such a powerful concept is that it applies across scales. You see it in the cooling of your coffee, the shuffling of a deck, the expansion of the universe. At the grandest level, the cosmos itself has an entropy budget. In its early moments, right after the Big Bang, the universe was in a remarkably low entropy state. Matter was evenly distributed, energy was smooth, fluctuations were tiny. Over time, as galaxies formed, stars ignited, and black holes grew, the entropy increased. The universe's story has been one of disorder rising, possibilities multiplying, records accumulating. Entropy is not just disorder, it's information. Every rise in entropy is a way of saying the universe has more possible states consistent with its current condition. In that sense, entropy is like the footnotes of reality, keeping track of the branching pathways, the spreading of possibilities. That's why Bekenstein's insight was so profound. By assigning entropy to black holes, he was saying they are part of the universal story, not exceptions to it. They don't erase the record, they add to it, in the most concentrated way possible. There's also a human angle here. When you look at your own life, you can see entropy playing out. The messiness of a room left unattended, the slow decay of objects, the difficulty of reversing accidents, all of these are entropy in action. But entropy also records. Every wrinkle in paper, every scratch on wood, every scar on skin is information, a trace of events. Disorder tells a story of what has happened. In that sense, entropy is memory, inscribed into the physical world whether we like it or not. If entropy tells a story, it's not one with a fixed script, it's probabilistic. Systems drift toward disorder not because they're forced, but because it's overwhelmingly likely. That's why shuffling a deck rarely returns it to order, though in principle it could. The entropy rise is the story of probability playing out, the universe favouring the many over the few. That's also why entropy is such a compelling link between physics and information theory. Information theory is about probabilities, choices, and possibilities. Entropy bridges the two, telling us that disorder is not just chaos, it's the proliferation of options. Returning to black holes, this perspective deepens the metaphor of cosmic librarians. They don't just store information, they preserve entropy, ensuring the second law holds even in the most extreme environments. The increase in horizon area when something falls in is the entropy increase, the record of the story being continued. The librarian doesn't forget, even when the book seems swallowed. The record is there, counted in Planck-sized patches of surface. Some physicists even argue that entropy is the foundation of space-time itself. The idea is that gravity might not be a fundamental force, but an emergent one, arising from the statistical behavior of microscopic information bits. In this view, entropy is not just a property of systems, it's the ground from which space-time emerges. If that's true, then disorder doesn't just tell a story, it writes the very stage on which the story unfolds. The story entropy tells is not always gentle. Entropy is the reason stars burn through their fuel, the reason heat spreads out, the reason life must constantly consume energy to maintain order. Without entropy's rise, time would lose its direction, processes would stagnate, and change itself might be impossible. But with entropy, the universe evolves, complexity arises, and history becomes possible. Disorder is the backdrop against which structure has meaning. Think about how a seed grows into a tree. The tree creates local order, arranging molecules into bark, leaves, and roots, but in doing so, it releases heat and increases entropy in its surroundings. Life thrives by exporting disorder, creating pockets of order at the cost of raising the entropy of the environment. That's not a loophole, that's the rule in action. The tree's growth is another story entropy tells, one that adds richness to the grander narrative of the universe's unfolding. The connection between entropy and information also invites reflection on knowledge itself. When you learn something new, your brain's neurons change state, connections strengthen or weaken. That's information being stored, entropy rising in the microscopic details of your brain. Your memories are not just personal, they're physical records, shaped by entropy's laws. Even forgetting is part of the story, as information disperses into less accessible forms. Disorder and memory are not opposites. They're partners in the narrative. In black holes, entropy is maximized, records are compressed, and stories are preserved in their most efficient form. That's why physicists see them as laboratories for understanding the universe's deepest principles. They show us entropy at the edge, pushed to its extreme, forcing us to confront the limits of information, and in doing so, they remind us that disorder is not emptiness, it's fullness, an abundance of possible configurations, a record of what has been and what could be. As we drift further into this understanding, entropy stops being just a number in equations. It becomes a voice, quietly narrating every process, every transformation, every scattering of molecules and collapse of stars. It tells the story of time's arrow, of the conservation of information, of the growth of disorder that nonetheless preserves memory. And through black holes, entropy tells us that even the most extreme environments cannot silence that story. When Jacob Bekenstein proposed his bound, and Stephen Hawking confirmed that black holes have entropy, a deeper question began to take shape. If the amount of information in a region of space depends not on its volume, but on the surface area of its boundary, then perhaps the universe is not what it seems. The world feels three-dimensional. We walk through length, width, and height. We build houses with rooms that have depth. We toss balls through open air. We move around in what seems like genuine volume. But if the fundamental bookkeeping of reality is done on surfaces, then those three dimensions may be illusions, projections, like images cast from a two-dimensional film. This startling thought led to the idea of holography, a principle that suggests our universe itself may work like a hologram. To make sense of this, think first about an ordinary hologram. You've probably seen them on credit cards or in novelty stores. A hologram is a two-dimensional surface, flat and thin, that contains information about a three-dimensional image. Shine light through it at the right angle, and suddenly you see depth, shape, perspective. A bird seems to hover, a globe seems to turn, a face seems to look back. The hologram is not the object itself, but the information encoded on the surface is enough to project the appearance of 3 dimensions. That's what makes the metaphor so powerful. If a sheet of plastic can carry the instructions for a 3D picture, maybe the surface of space can carry the instructions for the 3D world we experience. This idea is not poetic speculation. It was born from the stubborn mathematics of black holes. When you throw matter into a black hole, its surface area grows in precise proportion to the information swallowed. That means the surface encodes the story of what went in. But if the surface has enough information to describe the interior, then perhaps the interior is not fundamental at all. Perhaps what we call volume is just the projection of surface information, a holographic display written on the cosmic boundary. At first, this sounds outrageous. The room around you feels undeniably 3-dimensional. You can walk from one corner to another, stretch your arms, move up and down. Nothing about your senses suggests that this is a projection. But remember, the hologram you hold in your hand feels convincing too. Tilt it one way, and you see depth. Tilt it another, and you see perspective. Your brain interprets it as a genuine 3-dimensional scene, even though the underlying information is 2-dimensional. If physics is correct about the Bekenstein Bound, then reality itself may be doing something similar on a scale far beyond imagination. One of the first physicists to push this line of thought was Gerard 't Hooft, who in the 1990s proposed that the maximum entropy of a region, the Bekenstein Bound, implies a holographic description of nature. Leonard Susskind expanded on it, coining the phrase the holographic principle. According to this principle, the information describing a volume of space is stored not inside the volume, but on the surface that encloses it. Just as the black hole horizon encodes everything that fell in, the boundary of the universe may encode everything inside. It's important to be careful here. Holography doesn't mean we're living in an illusion, or that matter is fake. The 3-dimensional world you see and touch is real in every sense that matters to you. Holography is about the bookkeeping of fundamental physics. It says that the equations describing space, matter, and energy can be rewritten in a 2-dimensional form with all the same predictions and outcomes. It's like discovering a different language that expresses the same story. The fact that such a rewriting is possible tells us something profound about the structure of reality. The most striking example of holography comes from string theory, in a result known as the ADS-CFT correspondence, discovered by Juan Maldacena in 1997. In this correspondence, a theory of gravity in a certain curved spacetime called anti-de Sitter space is equivalent to a quantum field theory on the boundary of that space. Gravity inside is encoded by information outside. The holographic picture is exact, not just an analogy. Everything happening in the bulk, the interior, is reflected on the surface. This is the clearest demonstration yet that holography is not just a metaphor, but a real principle of physics. Why does this matter for you, listening in the dark? Because it changes how we imagine existence itself. If the universe is holographic, then the deepest truths are not hidden in the depths, but spread across the edges. Surfaces become the primary stage, and volumes are their shadows. It's an inversion of intuition. We grow up thinking the inside of things is what's real. The contents of the box, the core of the star, the bulk of the universe. Holography tells us the opposite. The edges carry the full story. The darkness of space is not empty depth, but projection, unfolding from the information etched into distant boundaries. This shift of perspective can be unsettling. It suggests that space is not what it seems, that depth is emergent, not fundamental, but it can also be comforting. Holography ensures that information is never lost, because the surface always records it. Even when black holes evaporate, even when stars collapse, the surface encoding preserves the data. The universe is not careless with its memory. The holographic principle is its guarantee. You can think of it like a cosmic cinema. Imagine sitting in a theatre watching a three-dimensional movie projected on a screen. You see landscapes stretching into distance, objects flying toward you, characters walking in depth. But you know that the movie itself is encoded on the two-dimensional film. The story exists on the surface, projected into your experience of depth. The universe may be doing the same with us. We live inside the movie, immersed in the three-dimensional drama, but the fundamental script is written on a cosmic screen at the edges of space. Some researchers even suggest that consciousness itself might be tied to this holographic nature. If reality is encoded on boundaries, perhaps our perceptions of depth, time, and continuity are the way our brains interpret the projected information. Just as the eye turns patterns of light into shapes and motion, perhaps the mind turns holographic encoding into lived experience. That doesn't diminish our world. It deepens it, telling us that our sense of immersion is part of a much larger process of projection. It's worth pausing to notice how radical this is. For centuries, people assumed space was just space, infinite and three-dimensional. Then Einstein showed that space and time are interwoven, bending under the influence of mass and energy. Now, holography suggests that even that curved space-time is not ultimate but emergent, projected from a deeper layer of information. Each shift has peeled back a layer of assumption, revealing a more subtle and intricate reality. And each shift has come from daring to ask, what happens to information? The darkness of space itself takes on a new meaning in this picture. When you look into the night sky, you see stars, galaxies, and the vast blackness between. That blackness feels like emptiness, like endless depth. But if holography is true, then the darkness may not be an infinite void at all. It may be the projection of surface information, a hologram of depth cast from the edges. The blackness is not nothingness. It's the unfolding of encoded detail, richer than we can fathom. This doesn't make the universe any less awe-inspiring. If anything, it magnifies the wonder. Imagine that every star, every galaxy, every particle of dust, every breath you take is part of a projection so intricate that it feels solid, deep, real. The scale of the encoding is staggering. To capture the information of even a small region of space requires a surface area tiled with Planck-sized patches, each carrying a few bits. Multiply that across cosmic horizons, and you begin to glimpse the unimaginable density of information written into the fabric of the universe. Holography also provides a way to resolve puzzles. If black holes are cosmic librarians, holding information on their surfaces, then the holographic principle extends that insight to the entire universe. Not just black holes, but all regions of space are surface recorders. Information is always preserved, always encoded, never lost in the depths. The universe itself is the grandest library. It shelves not in the bulk of space, but along the edges that define it. This principle continues to guide modern research. Physicists probe holography not just through black holes, but through quantum entanglement, quantum gravity, and cosmology. They search for evidence that space-time itself emerges from information, that the geometry we live in is the large-scale effect of microscopic bits woven together. If that's true, then information is not just a property of the universe, it is the foundation. The cosmos is not built of matter and energy alone. It is built of information, encoded holographically across its boundaries. As you lie back and let this sink in, it might feel almost dizzying. The floor beneath you, the air around you, the stars above you, all of it, in this view, is the projection of surface information, a cosmic hologram in which you are immersed. That doesn't diminish your reality, it affirms it, while also revealing a hidden layer beneath it. You are part of the projection, part of the code, part of the surface story unfolding in depth. And as this thought deepens, the next question emerges naturally. If information is encoded holographically on surfaces, then what are the fundamental units of that code? What is the smallest building block, the indivisible patch of surface that carries the story? When you hear the word bit, you probably think of computers. Ones and zeros blinking through circuits, lines of code scrolling across a screen, data stored in chips and drives. A bit is the smallest unit of information, a simple yes or no, on or off. Our entire digital world, from the songs we listen to the pictures we share to the conversations we type, is built on these elementary distinctions. It might be surprising, then, to realize that physicists also use the word bit when they talk about the universe itself, and not just metaphorically. According to the Bekenstein Bound and the holographic principle, reality itself may be written in bits, etched into the surfaces that define space. To appreciate how radical this is, consider first the Planck length. This is the smallest scale at which our known laws of physics make sense. It is about 10^35 meters, so small that no microscope, no particle accelerator, no imaginable device could probe it directly. At that scale, space-time is thought to be grainy, no longer smooth, fluctuating in quantum foam. Each square of surface with an area equal to the Planck length squared can hold just a few bits of information. It's as though the universe is pixelated at its edges, like an image made of dots so tiny that, from a distance, you don't notice them. This is where the Bekenstein Bound takes on its most concrete form. It says that the maximum amount of information that can be stored in a region of space is proportional to the area of its boundary, measured in these Planck-sized squares. Every square of area, every microscopic patch of the boundary, is a slot for a few bits. Add them together across the surface, and you get the total capacity for information inside. That is the bookkeeping system of the universe, a ledger written on the edge of reality. It's difficult to wrap the mind around this because we are used to thinking in terms of volume. A bigger box should hold more objects, more states, more information. But at the ultimate level, it's not the volume that matters, it's the surface. That inversion of intuition is why physicists speak of holography. Just as a two-dimensional hologram holds the information for a three-dimensional image, the two-dimensional boundary holds the information for a three-dimensional region. The bits are written on the edge, and the bulk is their projection. What makes this so fascinating is that these bits are not ordinary bits like the ones in your laptop. They are physical, tied to the structure of space-time itself. Each bit represents a fundamental degree of freedom, a possible yes or no encoded in geometry, quantum fields or entanglement. The surface of a black hole, for example, can be thought of as tiled with these bits, each one carrying a fragment of the story of what has fallen in. The horizon is not just a boundary in space. It is a storage medium, a cosmic hard drive at the limits of physics. Think about what this means for information. When you drop matter into a black hole, it adds entropy, increasing the number of microstates consistent with the black hole's macroscopic properties. That entropy is proportional to the increase in horizon area, which in turn means more Planck-sized patches, more bits on the surface. It's as though every new piece of matter adds new lines to the cosmic script, more information written into the boundary. The universe keeps meticulous records, never erasing, always expanding the library. This is not just about black holes. The Bekenstein Bound applies to any region of space. Imagine drawing a sphere in empty space. According to the bound, the maximum entropy inside is proportional to the surface area of that sphere, not its volume. You can try to pack more and more matter, more and more complexity inside, but once you reach the limit, the region collapses into a black hole, and the bound is enforced. Nature refuses to let you exceed the capacity of the surface. The bits are written only on the edge, and the edge has a finite number of slots. Some physicists see in this principle a profound clue about the nature of reality. If everything inside a region is encoded on its boundary, then perhaps space itself is not fundamental but emergent. Just as temperature emerges from the collective motion of molecules, just as pressure emerges from collisions in a gas, perhaps space and time emerge from the interplay of bits on a surface. In this view, the universe is not a stage in which events unfold. It is an illusion created by information, stitched together from binary distinctions at the smallest scales. This brings us to a striking realization. The universe might be finite in its informational capacity. Even though space seems infinite, even though we can imagine endless galaxies and stars, the amount of information that can be stored in any finite region is bounded. That means there are limits to complexity, limits to memory, limits to computation. You cannot build a machine that stores infinite data, because the cosmos itself won't allow it. The laws of physics impose ceilings, not just on energy and speed, but on information. It may feel strange to think of the universe as a kind of computer, but that analogy has grown stronger in recent decades. Physicists talk about the cosmos as if it were processing information, running on bits written into its structure. The equations of quantum mechanics are rules for how those bits evolve. The laws of thermodynamics are rules for how entropy counts them. The geometry of space-time is a reflection of how they are arranged. In this picture, existence itself is computation, the unfolding of information through the logic of physics. But if the universe is a computer, its bits are not etched on chips or silicon. They are written on horizons, on surfaces, on the edges of regions. That's why black holes are so central. They show us the limits of information, the ultimate density of bits. No object can hold more information than a black hole of the same size. The horizon is the perfect storage medium. Every Planck-sized patch filled, no slot wasted. That's why some call black holes the most efficient computers in existence. They saturate the Bekenstein Bound, maxing out the capacity of nature's ledger. This vision of bits on the edge also reshapes how we think about identity and memory. If everything about a system is encoded in its surface, then perhaps our own reality is part of that code. The particles that make up your body, the thoughts in your mind, the experiences you've lived, if they can be described in terms of information, then they too may be written into the holographic script of the universe. You're not just matter moving in space, you're information, preserved and bounded by the rules of cosmic encoding. It's natural to wonder what these bits look like. Do they correspond to quanta of geometry, to loops of space in some deeper theory of quantum gravity? Are they linked through entanglement, like threads of a vast web tying surface patches together? Physicists don't yet know. Different approaches offer different candidates, strings vibrating in higher dimensions, spin networks linking Planck-scale nodes, quantum entanglement shaping emergent geometry. But they agree on this. The bits are real, physical, measurable in principle, and essential to the story of reality. This realization also changes how we imagine infinity. If space is infinite, then perhaps the number of bits is infinite too. But in any finite region, the number is capped. You can't exceed the bound, no matter how clever you are. That means even the most advanced civilization, even with unimaginable technology, cannot escape the limits of information. They can approach the bound, fill the surface with bits, but they cannot go beyond. The laws of physics guard the boundary, enforcing the capacity. From a different angle, this is not limiting but liberating. It tells us the universe has structure, order, and consistency. Information is not arbitrary. It is disciplined, woven into surfaces, written in Planck-scale patches. The cosmos is not chaotic but organized, with rules that ensure balance. You can trust that information is preserved, that entropy grows, that the bits remain on the edge, unforgotten. As you reflect on this, it may feel abstract, distant from daily life. But the principle touches everything. The warmth of your tea, the light of the stars, the flow of time, all of it is bound up with entropy and information. The bits written on the edge of reality are not just a curiosity. They are the foundation on which everything rests. You are part of that foundation, your own experiences encoded in the universal script. And as the story continues, the question deepens. If bits are written on the edge, and surfaces encode volumes, then perhaps what we call reality is itself a projection. Perhaps the three-dimensional world we live in is the unfolding of surface information into depth and time. When you look at an object, whether it's a book in your hands, a stone in the garden, or a planet hanging in the night sky, the intuition is automatic. You believe that what matters most lies inside. The weight of the stone must come from its dense interior. The story written in the book resides on the pages bound within. The planet's core is where its real essence lies, molten and heavy beneath the crust. Our instinct is always to treat the bulk as fundamental, the inside as real, the surface as a boundary with little importance beyond separating what's in from what's out. But the mathematics of black holes and the strange reasoning that emerge from the Bekenstein Bound suggest otherwise. In physics, when a region of space is considered, the true limits of its information are not measured by the amount of volume it encloses, but by the area of the surface surrounding it. That means the surface is where the true measure of reality lies. It's a reversal of common sense, a shocking twist that turns the world inside out. To see how unsettling this is, think again about black holes. Imagine throwing a collection of objects into one, books, planets, stars, whatever you like. You might think the details of those objects vanish into the volume of the black hole, swallowed into its depth. But no. The entropy of the black hole, the measure of how much information it contains, depends only on the surface area of its horizon. That surface is where the record is kept. Nothing inside adds to the count, nothing beyond the surface changes the measure. The interior doesn't matter for the accounting. The surface is everything. This leads to the radical suggestion that the interior may not be fundamental at all. The inside is not the storage medium. The surface is. The depth is emergent, a projection, an illusion of perspective, while the true data is encoded on the edges. It's as though every object, every region of space, every black hole is a kind of sphere on whose skin the entire story is written. Peel away the bulk and you lose nothing of the information. Keep the surface and the essence remains. Consider how counterintuitive this is. You cut into an apple, and the richness of its structure is inside. The seeds, the fibres, the juice. The skin feels secondary, but in the logic of holography, the apple's reality is not contained in the juicy bulk. It's encoded on its surface, written in patches so small they defy imagination. The inside is a projection. The surface is the source. To make sense of this, the analogy of a hologram is useful once again. When you see a holographic image floating in space, you experience depth. You can move your head, and the perspective shifts just as it would with a real object. But you know the actual information is stored in the two-dimensional surface of the holographic plate. The depth is not fundamental, it's emergent, reconstructed by your perception from the encoded details on the surface. That's exactly what the Bekenstein Bound suggests about the universe itself. The interior of space, the volume we move through, might be like the apparent depth of a hologram, convincing, immersive, but derivative. The true encoding is on the boundaries. What makes this twist so important is that it forces us to rethink what real means. If the surface holds the data, then reality itself is a boundary phenomenon. The richness of the cosmos, the galaxies, the stars, the atoms, the living beings, are all part of a projection from the surface code. In this sense, we are inhabitants of a story written on the edge, actors in a play whose script is etched into horizons. The bulk of our world, everything we see and touch, is a manifestation of the deeper surface information. This is not just speculation, it has precise mathematical backing. The entropy of black holes grows with area, not volume. The holographic principle derived from this fact has been shown to hold in multiple theoretical frameworks, most famously in string theory's AD-CFT correspondence. There, the physics of a gravitational universe in the interior is exactly mirrored by a quantum field theory on the boundary. Every event inside is equivalent to an arrangement of information on the surface. It's not just a metaphor, it's a duality. The surface and the inside tell the same story, but the surface is the more fundamental description. Think about how this changes perspective on space itself. We usually imagine the cosmos as a vast interior, with galaxies scattered throughout like marbles in a box. But if holography is correct, then the box itself is the true source, and the marbles are projections. The edges of space carry the code, and the galaxies are its expression. The inside is not where reality resides, it is where reality appears. This twist also reshapes our understanding of limits. If you believe the interior was fundamental, you might expect that as you cram more matter into a region, the information stored should grow with the volume. But the Bekenstein Bound says no. It grows only with the area. Once you reach that cap, no more information can be stored, no matter how much bulk you imagine. The surface is the gatekeeper setting the ultimate constraints. That's why black holes are so central. They show the principle in its starkest form, saturating the bound, filling every surface patch with bits. There's something humbling about this idea. It means our intuition about objects built from everyday experience is deeply incomplete. We evolved to think of insides as essential because we interact with volumes, because we cut into fruit, because we feel the solidity of the world. But the fundamental layer of reality doesn't care about our intuition. It encodes the universe on surfaces, making the bulk secondary. Our senses grasp the projection, not the code. The shocking twist is that the surface is the true stage of reality. To draw this into something relatable, think of how memories are stored. You carry your life inside your brain, a vast web of neurons connected in intricate patterns. But from the perspective of physics, what really matters is the information, the pattern of firing, the bits of yes and no that describe your thoughts. The bulk of tissue is not the memory. The memory is in the configuration, the surface-level code of activity. The analogy is not perfect, but it points in the same direction. The inside is a medium for experience, but the true content lies in the patterns, the encoded information. The surface twist also invites deeper philosophical questions. If what we experience as volume is a projection, then perhaps our sense of depth, distance, and interiority are emergent properties of information processing. Space may not exist in the way we think. It may be the result of how information is structured, the illusion of depth conjured from surface bits. That doesn't make it unreal. It makes it emergent, like heat emerging from molecules or colour emerging from wavelengths. The inside is real to us because we live within the projection. But the underlying truth is that the surface holds the code. Physicists are still probing what this means. In holographic models, the geometry of space emerges from entanglement patterns on the boundary. Connections between bits on the surface weave together to create the illusion of depth. The tighter the entanglement, the closer the points seem inside. The looser the entanglement, the farther apart they appear. Space itself is geometry born from information. That's how the inside is constructed, from surface relationships, not fundamental volume. So when you look around, when you see the room, the stars, the world, you are gazing into a projection built from the surface code of reality. The richness of existence is the unfolding of information written on the edges. The shocking twist is that you are not living in the interior at all. You're living in the surface's story, immersed in its projection. If the surface holds the code, if the inside is emergent, then what happens when we approach the limits of that code? What happens when we try to exceed the capacity of the surface, to push beyond the bound? If you sit quietly with a cup of tea, letting the steam curl upward and the surface ripple faintly, it doesn't feel like an object carrying profound secrets about the nature of the universe. It feels ordinary, almost trivial, just a drink cooling slowly, waiting to be sipped. But from the perspective of physics, that cup of tea is more than a warm liquid in a vessel. It is a collection of countless molecules moving, vibrating, colliding, interacting in ways so detailed that the full description of what's happening inside would be unimaginably vast. The question that naturally follows from this is a playful one, but also profound. How much can a cup of tea remember? This isn't memory in the human sense. No diary of events written in words, no story consciously recalled. It's memory in the informational sense. Every system in the universe contains information about its state, and that information has limits. A cup of tea is not excluded from the rules of the Bekenstein Bound. It too has a maximum information capacity, determined not by the liquid's volume, but by the surface area enclosing it. Think about that carefully. Inside the cup, trillions upon trillions of water molecules bounce and jostle, their paths shaped by temperature, pressure, and interactions. You might assume that the complexity grows with the number of molecules, that the information scales with how much liquid fills the cup. But physics insists otherwise. The bound says the maximum entropy, the maximum information, is limited by the area of the cup's surface. No matter how deep the cup, no matter how much tea you pour in, the fundamental ceiling is set by the enclosing surface. The inside doesn't get to decide. The outside does. That means your cup of tea is more than an afternoon comfort. It is a microcosm of the universe's deepest principles. In it, you can glimpse the same logic that governs black holes, the same bookkeeping rules that apply to galaxies. If the cosmos is a library where the surfaces are the shelves, then your cup is a tiny book in that library, its surface carrying the limit of what can be recorded about its interior. Now, let's try to imagine the scale of this. Suppose the rim of your cup measures 10 centimeters across. The surface area enclosing the tea might be on the order of a few hundred square centimeters. If you divided that surface into plank-sized squares, each one about 1070 square meters, you would get an astronomically large number. Each square holds a few bits. Multiply it out, and you find that even a simple cup of tea has an information capacity greater than anything your mind can comfortably grasp, more than the digital memory of all computers on Earth, packed into the quiet boundaries of a drink. That number isn't meant to suggest you could somehow download the tea's information onto a hard drive. It's meant to show how the rules scale. The same logic that makes a black hole's entropy so immense applies in miniature to your cup. The surface sets the maximum. The bulk dances with molecules, but the bookkeeping is on the edge. What's fascinating is that this information isn't just abstract. It records the microscopic details of the system. Every flicker of a molecule, every quantum interaction, every vibration leaves its imprint. In principle, if you could read out the full information encoded on the surface, you would know everything about the tea's state, its temperature, its structure, its history. Of course, in practice this is impossible. The data is too immense, too scrambled, but the principle is there. The tea remembers, not in words, but in the physics of information. This perspective makes ordinary objects feel different. A stone, a chair, a glass of water, all of them are carriers of information, bounded by surfaces, encoded in bits too small to see. They are not mute or blank. They are records of themselves, written in entropy, constrained by the same bound that shapes stars and black holes. A cup of tea is not just a drink. It is a participant in the universal game of information, following the same rules as galaxies. There's something delightful about this scaling of physics. It reminds you that the profound is not confined to the distant or the exotic. You don't need to stare into the maw of a black hole to touch the Bekenstein Bound. You can hold it in your hands, feel its warmth, sip from it slowly. The principles that govern the cosmos are present in every object around you. The shocking twist that information scales with surface, not volume, is as true for a cup of tea as it is for the event horizon of a collapsing star. And it's not just static information. The tea's entropy rises as it cools, as heat flows from liquid to air, as order gives way to probability. That rise is the story of time written into the system. Each moment of cooling is a moment of remembering, of information spreading outward, of entropy keeping track of what has happened. You can think of the steam rising as a visible trace of the tea's memory leaking into the air, a signal that the story is still unfolding. Of course, no one will ever reconstruct the exact past of that cup. You can't rewind the entropy, can't reassemble the molecules into the same dance they had before. That's what makes the arrow of time feel so irreversible. But the principle is there, the cup remembers, and the record is inscribed in its surface capacity. The Bekenstein Bound ensures that the memory never exceeds what the surface allows. The tea is not infinite in its recall. It is finite, bounded, disciplined by the edges of reality. It's natural to wonder what this says about ourselves. If a cup of tea has an information capacity, so do you. Your body, your brain, your experiences, all of it is encoded in physical states, bounded by surfaces, limited by the same principles. You're not infinite in memory, you're bounded. But within that bound, the amount of possible information is immense, far beyond what you could ever consciously grasp. Your life is a finite but overwhelming record, inscribed in entropy, carried on the surface of your being. This doesn't diminish you, it places you in continuity with the cosmos. You and your tea and the black holes at the centers of galaxies all play by the same rules. You're not separate from the universe's bookkeeping. You're part of it. Your memories encoded in neurons, your body's entropy rising with time, your information bounded by the surfaces that enclose you. The tea is a mirror of your own condition, a small reminder of the universality of physics. If you think of the tea this way, it changes how you look at ordinary life. Nothing is trivial. Every object, no matter how simple, is part of the grand informational structure. The Bekenstein Bound doesn't apply only in rarefied circumstances. It's here, now, in the cup on your table, in the air you breathe, in the warmth of your body. You live in a universe where surfaces are sacred, where every edge is a ledger, where every cup remembers as surely as a black hole does. And this brings us closer to the next realization. If the surface sets the bound and the tea's memory is finite, then what happens when we reach the edge of memory in larger systems? What happens when we push the bound to its limits, filling every surface bit with information? When you think of a hard drive, the image that comes to mind is usually something small and familiar, a device tucked inside a computer or attached to a cable. It's a tool for storage, a place where documents, photos, music and memories in digital form are written in patterns of magnetic domains or solid-state cells. Each 1 and a 0 is a microscopic switch, a distinction that accumulates into libraries of data. We live in an age where these devices have become extensions of our own memory. We don't just remember with our brains anymore. We remember with machines, with cloud servers and drives filled with archives. But when physicists look at the universe through the lens of the Bekenstein Bound and the holographic principle, the metaphor grows larger, almost absurd in scale. They begin to describe the cosmos itself as a kind of hard drive, a system whose capacity is not infinite, whose storage is written in bits on surfaces, whose memory is encoded in the very fabric of space-time. Just as your hard drive has limits, so many gigabytes, so many terabytes, the universe too has limits, measured not in familiar digital units, but in entropy bounded by area. This idea is more than playful analogy. It emerges from serious reasoning about how information behaves. Every physical system is a register of information. The tea in your cup holds it. A star blazing in the sky holds it. A black hole collapsing in silence holds it. Each is part of a universal accounting, where the maximum storage capacity is dictated by surface area. Put them all together, and you realize the entire cosmos is like a vast memory device, a ledger of everything that has ever happened, written in bits no one can see directly, yet real enough to constrain all events. It's worth pausing to consider what a hard drive really does. When you store a photograph, the file is reduced to a sequence of bits, each representing some detail about colour, brightness, and position. Those bits are arranged physically on the drive, magnetic fields flipped one way or another, electrons trapped or released in tiny cells. The photograph is not stored as an image, but as an arrangement of differences, a string of binary values. When you view it again, the system reconstructs those differences into the picture you recognise. The image emerges from the code. Now translate that into the language of the universe. Every physical system is like a file. The bits are not magnetic flips or electron traps, but fundamental distinctions in quantum states, written on the boundaries of space. Those bits don't look like anything to us. They are not images or text, but when they interact and evolve, they reconstruct the world we live in. The stars, the galaxies, the planets, and ourselves emerge from those distinctions. We are the picture reassembled from the code. The universe is the hard drive. We are the files, the processes, the outputs of its storage. If this sounds abstract, return to black holes for clarity. They are the ultimate demonstration of storage capacity. A black hole doesn't care what falls in. A planet, a photon, a cloud of gas. The details vanish into the horizon. What remains is entropy, proportional to surface area, the maximum number of bits that can be written on the edge. Black holes are full drives, devices that have reached their capacity, saturated to the last bit. They don't overwrite or delete in the way human technology does. They keep the information encoded, even if scrambled beyond recognition. They are nature's demonstration that no system can exceed the bound. Think now about scaling this principle to the universe itself. Our cosmos has horizons too, cosmic horizons beyond which light cannot reach us. Those horizons define surfaces, and those surfaces define limits. The observable universe, the patch of cosmos we can see, has a finite area, and therefore a finite number of bits. That means the total amount of information that can be stored in our observable universe is not infinite but capped, like the storage on your device. The number is staggeringly large, incomprehensible in everyday terms, but it is not boundless. The universe is a finite drive, not an infinite one. This raises strange and fascinating questions. If the cosmos is a storage device, what is being written into it? The answer is everything. Every event, every interaction, every fluctuation is part of the unfolding record. The movement of galaxies, the birth of stars, the flow of energy, the rise of life. All of it adds to the entropy. All of it is encoded on the cosmic surface. We may never be able to read that record in any direct way, but physics assures us that the information is preserved, never lost, never erased. The cosmic hard drive is not careless with its data. The metaphor also highlights the difference between our perspective and the universe's perspective. To us, events come and go. A conversation is spoken, then fades. A star burns, then collapses. A life begins, then ends. But in the language of information, each event leaves an imprint, increasing entropy, adding bits to the record. Nothing is truly gone. The cosmic drive stores it all, even if it is forever scrambled beyond retrieval. That permanence is both haunting and comforting. We may lose track of the past, but the universe does not. It keeps the ledger intact. Another interesting dimension to this metaphor is the possibility of compression. Human technology uses clever algorithms to compress files, to store the same data with fewer bits by recognizing patterns and redundancies. Could the universe be doing something similar? If the laws of physics are deeply mathematical, perhaps the cosmic drive doesn't need to store every detail separately. Perhaps it encodes reality in patterns, symmetries, and rules that act as compression algorithms. From simple principles, complex outcomes unfold. That may be why a finite number of bits can still describe a universe so vast and detailed. The idea of the cosmos as a hard drive also leads naturally to thoughts about computation. A computer doesn't just store bits, it processes them. It runs algorithms, changes states, evolves data over time. In the same way, the universe doesn't just hold information statically, it processes it, according to the rules of physics. Each second is like a new operation, each interaction a new update. The cosmos is not just storage, it is computation in action, a processor working with the bits written on its surfaces, evolving them into the story we experience as time. That view aligns with the work of thinkers like John Wheeler, who coined the phrase "it from bit." He suggested that everything physical arises from binary distinctions, from answers to yes or no questions. In this view, the universe is not built from matter and energy alone, but from information, with matter and energy being the emergent results of informational processes. The cosmic hard drive is not a metaphor then. It is the essence of reality. Existence itself is memory in action. This perspective also reshapes how we think about finiteness. Many people imagine the universe as infinite, endless in space and time, without bounds. But the Bekenstein Bound suggests a more disciplined picture. Every region is finite in capacity, every horizon sets a ceiling, every surface holds only so many bits. Infinity may be an abstraction, not a reality. The cosmos is large beyond comprehension, but not infinite in storage. That subtle difference matters. It means there are limits to complexity, to knowledge, to computation. Even the grandest scale is constrained by surfaces, and yet, within those limits, the richness is staggering. The cosmic drive may not be infinite, but its capacity is more than enough to contain galaxies, life, thought, and wonder. Just as your computer's drive can hold entire libraries, entire lifetimes of photographs and music, so too can the universe's drive hold entire histories of stars, worlds, and beings. The finiteness does not diminish the grandeur, it makes it more remarkable. That all of this, the beauty of a night sky, the complexity of a human brain, the depth of time, fits within the ledger of surface bits is extraordinary. As you reflect on this, you may find it unsettling to think of yourself as data on a cosmic hard drive. But consider the alternative. If the universe truly had no structure, no bound, no ledger, then nothing would be preserved, nothing would be consistent. Information could vanish without trace, entropy could behave arbitrarily, laws could shift. Instead, the universe is ordered, disciplined by the bound, encoded in a drive that never loses track. Your existence is not ephemeral chaos. It is part of a record that endures, woven into the memory of the cosmos itself. If the universe is a hard drive and its memory is written on surfaces, then how does that connect to the flow of energy and the laws of thermodynamics? How does the processing of information tie into the conservation of energy and the unfolding of time? Energy is one of those words that feels obvious until you pause to ask what it really means. We say we're full of energy in the morning. We talk about power plants producing energy. We describe the sun as a source of endless energy for life. In physics, energy has a very precise role. It is the conserved quantity that threads through every process, the measure that cannot be created or destroyed, only transformed. It is the bookkeeping of the physical world. But when you look closer, energy does not stand alone. Tied to it, often in ways that are subtle but fundamental, is information. The two are not separate domains, but deeply entangled aspects of reality. To understand this connection, imagine a simple physical system, like a box of gas molecules. Each molecule zips around, colliding, changing direction, sharing momentum. The total energy of the gas is the sum of all those motions. That's what a thermometer measures when it reads temperature, the average kinetic energy of molecules in motion. But there's also another story hidden in the gas, the information about the exact positions and velocities of those molecules. In principle, if you knew all those details, you would have a complete description of the system. That information is not independent of the energy. It is shaped by it, constrained by it, and revealed through entropy. Entropy is the bridge. It is both a thermodynamic quantity linked to energy and a measure of information. When you say a system has high entropy, you mean it has many possible microstates compatible with its overall energy. You don't know exactly which arrangement of molecules exists, only that the total energy fixes a set of possibilities. Entropy is your ignorance in bits, and at the same time it is the physical property that governs heat flow, efficiency, and time's arrow. Through entropy, energy and information meet. They are two sides of one coin, one describing the dynamics of systems, the other describing the knowledge of their states. One of the clearest examples of this connection comes from the idea of Landauer's principle. In the 1960s, physicist Rolf Landauer showed that erasing one bit of information has an unavoidable energy cost. Every time you reset a memory register, clearing it to zero regardless of its previous state, you must release heat. Specifically, at least kTln2 of energy, where K is Boltzmann's constant, and T is the temperature of the environment. That means information is not abstract. It has thermodynamic weight. Bits are physical. To process them is to spend energy. To erase them is to heat the world. This principle connects your laptop to the cosmos. Every computation you perform requires energy. Every decision made by a machine is grounded in thermodynamics, and the same principle applies to black holes, to horizons, to the universe itself. The bits written on the surfaces of reality are not free. They are bound to energy, to entropy, to the flow of time. You cannot separate them. You cannot have information without the energetic processes that sustain it. Consider black holes again, since they are the most striking laboratories of this relationship. A black hole has energy, measured in its mass. It also has entropy, measured in the surface area of its horizon. Those two are linked by the laws of thermodynamics extended into gravity. The famous first law of black hole mechanics says that the change in energy of a black hole is related to its change in surface area, with temperature and entropy entering the equation. It is not just a metaphor. Black holes truly behave like thermodynamic objects. They have heat, entropy, energy, and information all tied together in one fabric. The link between energy and information also clarifies why the Bekenstein Bound exists. If you try to cram too much energy into a region, you inevitably create a black hole. That black hole has a surface area, and therefore a maximum entropy. The energy cannot increase without bound, because the entropy cannot increase without bound. The limit on information is enforced by the limit on energy. The two march in step, never drifting apart. This raises a fascinating possibility. Perhaps what we call energy is itself just a way of talking about information in motion. Or perhaps what we call information is simply energy described in terms of possibilities. Some thinkers suggest the two are not distinct at all, but different languages for the same reality. Information theory and thermodynamics might be two views of a single coin, one counting states, the other counting transformations. From this perspective, the universe's great story, the expansion of space, the burning of stars, the rise of complexity, is also an information story. Each transformation of energy is accompanied by a rewriting of information. Each increase in entropy is both heat and ignorance, both thermodynamic necessity and informational bookkeeping. When you feel warmth from the sun, you're not just receiving energy. You're also receiving information about the state of a fusion furnace 93 million miles away. The photons carry both energy and knowledge, encoded in their frequencies and directions. Even in everyday life, this link is visible if you look carefully. When you charge your phone, you're not only moving energy into a battery, you're preparing it to process and store information. When you speak, the vibrations of air molecules carry both sound energy and the information of your words. When you breathe, oxygen molecules deliver chemical energy to your cells, and those molecules also carry information about the environment that created them. Every exchange is double-sided, carrying energy and information together. This duality has implications for the limits of knowledge. Because energy and information are bound, you cannot extract information without paying an energy cost. Measurement, observation, recording. All of these require energy. Your brain consumes glucose not just to keep you alive, but to process the information of your senses, to maintain memory, to think. Knowledge is never free. It is powered, sustained by energetic transformations. The physics of information is the physics of life itself. The meeting of energy and information also shapes the future of technology. Computers are limited not only by their design, but by thermodynamics. As we make them smaller and faster, the energy cost of processing each bit becomes more significant. Landauer's principle looms as an unavoidable flaw, a reminder that even at the edge of efficiency, you cannot separate the processing of bits from the dissipation of heat. Future technologies like quantum computers are attempts to play with this boundary, to harness quantum states that may allow new ways of encoding and processing information. But the tie to energy remains. No matter how exotic the device, it must obey the laws of physics that bind energy and information together. At cosmic scales, the same principle may limit what civilizations can achieve. A super-advanced society might imagine building vast computers the size of stars or galaxies. But the Bekenstein Bound and Landauer's principle would still apply. The amount of information they could store would be capped by the surface area of their systems. The amount of processing they could perform would be tied to the energy available. No level of advancement can escape the link. The ceiling is universal. There's also something profound in how this link touches the arrow of time. Energy transformations are irreversible in practice, and entropy grows as possibilities spread. That irreversibility is the story of information becoming less accessible, of knowledge fading into heat. Time itself may be nothing more than the unfolding of this relationship, the constant rewriting of information as energy disperses. You feel time not because a cosmic clock ticks, but because entropy grows, because energy and information dance in a one-way rhythm. Seen this way, the universe is not just a place of matter and forces, it is a place of messages. Every photon, every vibration, every fluctuation is a carrier of both energy and information. The cosmos is a vast communication system, endlessly transmitting, never silent, every corner filled with signals. We may only interpret a tiny fraction of those signals, but the rest are there, encoded in the fabric of space and time. The energy of the stars is also their story, written in light. The heat of the earth is also its history, written in entropy. And so, when you ask what happens when energy meets information, the answer is everything happens, reality happens. The two are not separate forces that occasionally intersect. They are inseparable aspects of the same foundation. To exist is to have energy, and to have energy is to carry information. The universe cannot have one without the other. This realization leads naturally to another question. If energy and information are bound, then perhaps our understanding of the cosmos as a whole must shift. Perhaps space itself, the geometry we inhabit, is not fundamental, but emergent from the way information and energy interact. When you shrink your view of the universe down to the smallest scales, to the level where atoms and particles rule, the neat predictability of the classical world begins to dissolve. Objects no longer follow definite paths, certainty slips into probability, and the rules of quantum mechanics take over. At first, this world seems chaotic and disconnected, a place where randomness is the only law. But then a deeper pattern reveals itself, something that unsettled even the sharpest minds of the last century: entanglement. Entanglement is the phenomenon where particles that once interacted become linked in such a way that their states are no longer independent. Measure one, and you instantly learn something about the other, no matter how far apart they are. Albert Einstein once called it spooky action at a distance, uneasy with the idea that a decision made here could determine an outcome there without anything physical travelling between them. Yet experiments have shown again and again that this is real. Quantum systems are not isolated, they are tangled, bound by correlations that defy ordinary notions of separation. To see why this matters for information, think of a pair of entangled particles as a message written across 2 pages. Neither page makes sense alone. Each is filled with symbols that seem random, but if you overlay them, suddenly the message becomes clear. The information is not in one particle or the other, it is in the correlation between them. That correlation can stretch across meters or light years, and it remains intact until the system is disturbed. Entanglement is information stored in relationships, not in isolated objects. This is the first hidden message of quantum mechanics. The universe does not store its information in neat little boxes, each independent of the other. It stores it in webs of connection. Entanglement is not an exception, it is the rule. The more we probe quantum systems, the more we find that particles are deeply linked, their states interwoven into networks of correlations. The cosmos is less like a collection of separate things and more like a tapestry, where the meaning lies in the threads that connect rather than in the threads alone. Now think about what this implies for space itself. In holographic theories, the geometry of space, the very notion of distance and location, emerges from entanglement. Imagine you have a large collection of particles entangled with each other in various ways. If the entanglement is dense and structured, the particles behave as though they are close together in a smooth geometry. If the entanglement weakens, the geometry appears to stretch. If it breaks, the geometry falls apart like tearing the fabric of space. Distance in this picture is not fundamental. It is a measure of entanglement. Where correlations are strong, closeness exists. Where they fade, separation grows. This is the second hidden message. Space is not a backdrop on which particles exist. It is a construct that arises from their informational links. Geometry is entanglement made visible. Your sense of being here, in a room, in a universe of depth, may come from patterns of quantum connections written in bits you cannot see, correlations you cannot directly measure, but which give rise to the stage on which your life unfolds. It's strange to think of space as something that could dissolve if the entanglement changed, but that's what these ideas suggest. Just as water vapor can condense into liquid or freeze into ice depending on temperature and pressure, space itself may be a phase of entanglement, a state of information that emerges under certain conditions. The solidity of the world is not guaranteed by a background stage. It is guaranteed by quantum relationships. There are experiments hinting at these ideas, though they are still indirect. Physicists explore how entanglement entropy behaves in quantum systems, how the spread of correlations mimics the growth of space. In some theoretical models, entire universes can be reconstructed from entanglement patterns alone. The message is consistent. The tangles are not peripheral. They are the foundation. Without them, space and time would have no stage to exist upon. This leads to another profound realization. If entanglement is where information hides, then the most fundamental secrets of the cosmos may not be located in objects, but in the invisible threads that connect them. Hidden messages could be encoded in these correlations, unreadable by looking at one system alone, but revealed when the systems are considered together. This is already true in quantum cryptography, where information is stored in entangled states that cannot be intercepted without breaking the link. It may also be true at cosmic scales, where the structure of space-time itself is the ultimate hidden message, arising from entanglement we do not yet fully understand. Consider again a black hole. For decades, physicists puzzled over how information could escape its grasp. If nothing can leave, and if the interior is inaccessible, does the information vanish? That seemed to break the rules of quantum mechanics. The emerging resolution suggests entanglement is the key. The particles radiated from the black hole in the form of Hawking radiation are entangled with what remains, carrying correlations that encode the lost data. The information is not gone. It is woven into the links between what escapes and what stays behind. The black hole does not destroy information. It scrambles it into tangles and spreads it out across the universe. That scrambling itself is fascinating. It suggests the universe does not simply keep information like a neatly labelled file. It mixes it, hides it, diffuses it into correlations so complex that recovering it is practically impossible. And yet in principle, it is always there. The cosmic hard drive never deletes. It hides, encrypts, and disperses. Entanglement is one of its favourite methods, ensuring that what seems random is in fact connected, that what seems lost is merely encoded in ways we cannot easily see. You might wonder if entanglement has any role in your everyday life. The answer is that it does, though indirectly. The stability of matter itself depends on quantum principles. The chemical bonds that hold molecules together rely on entanglement of electron states. The solidity of objects, the ability of your body to exist as a coherent form, depends on the invisible tangles of quantum fields. Without them, matter would not hold, atoms would not persist, and space would not emerge as the stage we inhabit. Every breath you take, every step you make is supported by the hidden web of entanglement threading through the universe. This perspective changes how you might think about separateness. We live as though we are isolated beings, each with our own boundaries, our own experiences, our own place in space. But quantum mechanics whispers a different message. You are not separate. At the most fundamental level, you are entangled with the rest of the cosmos. Your atoms were forged in stars, your molecules entangled in interactions that stretch across time. The information that makes you possible is not confined to your body. It is part of a universal web, a tangle of hidden messages written into existence itself. This doesn't mean your individuality is an illusion. It means individuality is a perspective, one layer of description on top of a deeper truth. At the base, reality is correlations. At the surface, it is objects. Both are valid, but one gives rise to the other. The hidden messages of entanglement are the foundation upon which the visible world is built. And as you reflect on this, the question grows larger. If space is built from entanglement, if information hides in tangles, then what does this say about the ultimate limits of knowledge? Are there messages in the correlations we have not yet learned to read? Could the very laws of physics themselves be emergent codes, patterns that arise from a deeper entangled foundation? If so, then our search for truth is not about discovering objects, but about deciphering connections. The answers are not in things, but in the webs that bind them. The thought naturally leads toward philosophy as much as physics. Entanglement challenges the idea of separateness, suggests that identity and location are emergent, and hints that reality itself is relational at its core. It says that what you call you and what you call the universe are not cleanly divided. They are entangled, woven into one fabric. That fabric carries hidden messages waiting to be unravelled, and in every attempt to study it, to measure it, to interpret it, we add to the record, we contribute new tangles, we deepen the story. If entanglement is the foundation, if hidden messages shape space and time, then how do those messages limit what we can know? What happens when the tangles themselves run into the constraints of the bound, when correlations push against the ceiling of capacity? There is a familiar feeling that comes when we reach for answers. It is the sense that, if we only worked a little harder, asked the right question, built the right tool, we might understand everything. This is part of what makes human beings so restless and inventive. We are driven by curiosity, by the desire to take apart mysteries and see how they work. But as physics teaches us, there are boundaries to what can be known, not only because of practical limitations, but because reality itself enforces them. The Bekenstein Bound is one expression of this. It says there is a maximum amount of information that can be stored within any region of space, defined not by its volume but by its surface area. That fact sets a ceiling on what knowledge is even possible. Think about what this means for our ambitions. We have built telescopes that look back billions of years, microscopes that peer into the structure of atoms, and detectors that sense vibrations in space-time itself. With each step we see further and deeper, convinced that the next layer of detail will reveal the ultimate truth. Yet the bound says that even if you had perfect instruments, flawless access, you could not know more than the maximum number of bits encoded on the surface of the system. There is no unlimited storage to be unlocked. The cosmos has already decided the limits. This becomes even clearer when you consider quantum mechanics. Heisenberg's uncertainty principle tells us that we cannot know both the position and momentum of a particle with unlimited precision. The more accurately we pin down one, the less accurately we can know the other. This is not a flaw of measurement, it is a law of nature. Information about reality comes with built-in trade-offs. It is impossible to reduce uncertainty to zero. Combined with the Bekenstein Bound, this means knowledge is not only finite but distributed in ways that we cannot fully capture. Some details are forever out of reach. We are used to thinking of science as a march toward completeness, as if one day a grand theory could explain every detail of existence. But these limits remind us that completeness is not possible. Our theories can be powerful, predictive, and elegant, but they will never fully exhaust the informational content of the universe. The ledger is too vast and the rules forbid total access. The cosmos is not a book we can finish reading. It is a book with pages we cannot turn, words we cannot see, and margins we cannot cross. At first, this might sound discouraging, but in another way, it is liberating. The recognition of limits gives us perspective. Knowledge is precious precisely because it is finite. Each discovery is a victory against ignorance, but never a conquest of it. Each new tool opens doors, but never all of them. The pursuit continues, not because it can be completed, but because it can never be completed. The horizon recedes as we walk toward it, ensuring that curiosity never runs dry. Take, for example, our attempts to probe black holes. For decades, they were thought of as objects that consumed information and never returned it. If true, that would mean a violation of quantum mechanics, a loss of knowledge that contradicts the principles of physics. The so-called information paradox emerged as one of the deepest puzzles. Slowly, through the work of many thinkers, the paradox shifted toward resolution. Information is not destroyed, it is scrambled, encoded, entangled, dispersed. But while we can be confident the information is preserved, we also know we will likely never be able to reconstruct it. The patterns are too complex, the tangles too dense. In theory, the knowledge exists. In practice, it is lost to us. The bound is not broken, but our hands cannot reach the ledger. Even outside of black holes, the principle holds. The observable universe itself has a horizon. Beyond a certain distance, light has not had time to reach us. Those regions are forever hidden, not because they do not exist, but because the structure of space-time places them outside our causal reach. No telescope, no matter how advanced, can see beyond that horizon. The information there exists, but it will never be available to us. The cosmos contains secrets we cannot uncover, not for lack of ingenuity, but by definition. Closer to home, the same principle applies. Imagine trying to capture the full informational content of a simple glass of water. Every molecule, every vibration, every fluctuation encoded in detail. Even if you had a computer the size of the Earth, the number of bits required would exceed what could be stored. The full ledger of that glass is beyond human capacity. We can describe averages, probabilities, emergent behaviors, but not the complete microstate. The bound sets a ceiling, and practical limits sit much lower still. These realizations change how we think about knowledge itself. Perhaps the goal is not to know everything, but to know enough to live, to act, to wonder. Physics becomes not a path to total mastery, but a dialogue with limits, a way of learning what can be known and what must remain mysterious. The limits are not failures. They are part of the structure of reality. They ensure that the universe retains depth, that it cannot be exhausted by calculation, that it remains larger than us no matter how far we reach. There is another dimension to these limits that touches directly on human life. Our brains themselves are physical systems, bounded by the same principles. Each neuron fires or stays silent, carrying bits of information. Each synapse can strengthen or weaken, encoding memory in chemical form. But the total number of neurons is finite, the connections finite, the storage finite. Your mind is powerful, but it is not infinite. The Bekenstein Bound applies to you as much as to stars and black holes. There is only so much that can be remembered, only so much that can be processed. Forgetting is not a flaw. It is part of the physics of being human. And yet, within that finiteness, richness abounds. Just as the universe's surface can encode galaxies, your mind can encode lifetimes of experience. Limits do not erase beauty. They frame it. The boundedness of knowledge makes each memory valuable, each discovery meaningful, each moment irreplaceable. You will never know everything, and that is why knowing something at all feels like a gift. This perspective also reshapes how we think about the future of science. As technologies advance, we may build machines that extend our reach, that process information on scales beyond human capacity. Artificial intelligence, quantum computers, planetary-scale observatories, all of these are attempts to push against the boundaries. But even they will encounter ceilings. No matter how powerful, they will still be subject to the bound. The dream of infinite knowledge will remain out of reach, because infinity is not part of the ledger. Instead, what we will find are new kinds of approximation, new layers of description. Just as thermodynamics gave us ways to understand gases without tracking every molecule, future theories may give us ways to understand the universe without tracking every bit. We will trade completeness for elegance, precision for patterns, detail for meaning. Knowledge will grow, but it will grow within walls we cannot climb. That is not defeat. That is the nature of the cosmos. As we accept these limits, the question becomes, what does it mean to live in a universe where knowledge is bounded? Does it change how we pursue curiosity, how we value discovery, how we see ourselves? Perhaps it teaches humility, reminding us that no mind, no machine, no civilization can ever know it all. Perhaps it teaches patience, since the search is endless and rushing brings no end. Perhaps it teaches wonder, because mystery is permanent, not temporary. The universe is not waiting to be solved. It is waiting to be engaged, experienced, and respected for its depth. And just as we come to terms with these limits, we are led to another thought. If knowledge is finite, if every system has a ceiling, then infinity itself must be re-examined. For centuries, infinity has been a powerful idea, used in mathematics, philosophy, and cosmology. But physics hints that infinity may not be real. It may be an abstraction, a tool of thought, not a property of the world. The bound suggests that even the cosmos is finite in its informational content. What does that mean for our imagination of endlessness? Infinity is one of those words that slips easily into our language. We use it casually to describe things that feel too large to count or too vast to imagine. Children will say they love something to infinity and beyond, as though the endlessness itself is a measure of depth. Mathematicians build entire systems on infinities, distinguishing between different sizes of them, proving that some infinities are larger than others. Philosophers lean on infinity as a way to speak about eternity, perfection, or the absolute. And when we think of the universe, infinity often enters as a default assumption. Space stretches forever, time runs without end, possibilities are limitless. But physics has a way of taming ideas that feel boundless. The Bekenstein Bound is one of those taming tools. It suggests that infinity may not describe the physical world as well as we think. If every region of space has a finite capacity for information, then infinity does not live in the details of the cosmos. It is a useful abstraction, but not a literal feature. Just as you can draw a perfect circle on paper, but never find one in nature, you can speak of infinity in equations, but never encounter it in reality. Consider how often infinities appear in physics. When early quantum field theories were developed, calculations often exploded into infinite results. Probabilities would sum to infinity. Energies would diverge without limit. These infinities were not signs of reality, but of broken reasoning. They had to be tamed by renormalization, by methods that trimmed away the impossible and left behind the physically meaningful. Infinity was the error signal, the reminder that the framework had gone too far. The real world does not diverge. It remains bounded. The same pattern appears in cosmology. It is tempting to imagine space as extending forever in every direction, time as stretching without beginning or end. But when we measure the universe, we see horizons. We see a finite age, about 13.8 billion years. We see an observable region bounded by the distance light has travelled since the beginning. Beyond that, perhaps space continues. But whether it does or not, what we can access is finite. The infinity is not available to us. It is not written into our physics. It is an assumption we project onto the unknown. There is also the issue of energy. If the universe were infinite in every sense, energy densities would create paradoxes. An infinite static universe would collapse under its own gravity, or expand without end in unstable ways. The finite age, finite density, and finite horizons are what allow our cosmos to be coherent. Infinity is not needed for reality to function. In fact, it may be too generous, too careless, a kind of overshoot in our attempts to imagine scale. This doesn't mean infinity is meaningless. In mathematics, it is powerful. Calculus depends on the ability to consider infinitesimal steps and infinite sums. Geometry leans on lines that extend without bound. Infinity is a tool for abstraction, a way to capture processes without limit. But when we turn back to physics, we have to be careful. The world is not an abstraction. It is concrete, and the evidence suggests it is constrained. Even in the smallest things, infinity gives way to bounds. You might think you can keep dividing matter forever, cutting pieces smaller and smaller without end. But quantum mechanics halts the process. Below certain scales, particles lose their individuality. Wave functions blur, and the notion of smaller divisions breaks down. There is a Planck length, a Planck time, thresholds beyond which the concept of further subdivisions ceases to make sense. Infinity promises endless divisibility. Physics denies it. There's a similar story in computation. Mathematicians can write algorithms that run infinitely, sequences without termination. But real computers, built from matter and energy, cannot. They are constrained by memory, by power, by thermodynamics. There is no infinite loop in practice. Eventually the system runs out of storage, overheats, or breaks down. Infinity is a concept of thought, not a property of machines. Since the universe itself seems to behave more like a computer than a blank canvas, the same lesson applies. Infinity is not embedded in its architecture. The holographic principle underscores this. It says the information in any region is proportional to surface area. That means you can never have infinite detail in a finite space. A single cubic centimetre of reality does not contain infinite data. It contains only as many bits as its surface allows. That is a number that can be written, if not easily grasped, and it is always finite. Infinity, once again, is too generous. And yet, the allure of infinity persists. It feels natural to think of stars without end, galaxies stretching endlessly outward, universes stacked upon universes. Perhaps that says more about the human imagination than about reality. We are comfortable with exaggeration, with extremes, with ideas that go beyond what is possible. Infinity offers a sense of completeness, a sense that nothing is missing. But physics shows us that boundaries exist, and those boundaries are what make structure possible. Without them, no pattern could form, no system could persist, no order could arise. This realization can reshape how we think about existence. If the universe is finite in information, then it is more like a novel than a blank page. A novel has a certain number of words, a certain number of pages. It can be long, complex, layered with meaning, but it does not go on forever. Its value lies in its form, in the way the limits shape the story. The cosmos may be the same. It does not need infinity to be vast or profound. It needs only to be rich within its bounds. There is also something more personal in this. We sometimes dream of immortality, of infinite time to learn, grow, or experience. But just as the universe cannot hold infinite information, we cannot live infinite lives. Our moments are finite, our memories are finite, our experiences are finite, and yet, within those limits, we find meaning. The bound does not diminish value, it frames it. If life were endless, perhaps meaning would dissolve. Because it is finite, it feels urgent, precious, and real. The universe mirrors that truth. Still, some physicists and philosophers hold out hope that infinity has a place in the deepest structure of things. Perhaps the multiverse contains infinite regions, each with different laws. Perhaps time cycles endlessly, without beginning or end. Perhaps new universes are born infinitely. These are speculative ideas, not yet grounded in evidence, but they keep infinity alive in conversation. Whether those infinities are real or only imagined, the bound remains within each region, each horizon, each accessible patch. Even if infinity exists in some higher sense, it is not accessible to us. It is not written into the surfaces we can read. So why say that infinity is too generous? Because it promises more than reality delivers. It suggests boundlessness where there are bounds, endlessness where there are endings, and perfection where there are limits. It is a beautiful idea, but physics teaches us that beauty often lies in finiteness, in the structure that constraints provide. Infinity is the dream. Finiteness is the reality, and that reality is no less grand for being bounded. When you begin to see the universe this way, new questions arise. If infinity is not real, what happens when we imagine scenarios that try to break the bound? What if we tried to push information beyond its limits, to cram more bits into a region than its surface allows? Would the universe resist? Would it collapse into new forms? The idea of breaking the bound leads naturally to thought experiments about what might happen when the rules are strained, when the ledger is tested to its extreme. When you hear that the universe places a strict limit on the amount of information that can fit into any region, it is natural to wonder what would happen if we tried to ignore that. Could the bound be broken? Could we imagine scenarios where more bits are packed into a region than its surface area should allow? This is not just idle curiosity. Physicists ask such questions often, because in testing the edges of the rules, they sometimes discover the deeper reasons those rules exist. Start with a thought experiment. Imagine a box, a simple cube floating in space. Inside it, you begin adding particles. At first, this is easy. The box fills with atoms, photons, electrons, and the information needed to describe them grows. You keep going, adding more, pushing the density higher. Eventually, though, something happens. The more energy you put inside, the stronger the gravitational pull becomes. When the energy exceeds a certain point, the box collapses into a black hole. Instead of overflowing with infinite detail, the system simplifies. The information is now proportional not to the volume of the box, but to the area of the horizon surrounding the black hole. The attempt to break the bound has failed. The universe responds by enforcing the rule in the most dramatic way possible. This is the central reason the bound exists. Gravity prevents it from being broken. The moment information storage exceeds the allowed maximum, gravitational collapse takes over, restoring the balance. It is as if the universe has a fail-safe, a mechanism that ensures the ledger never grows beyond the surface limit. You cannot cheat the system. You can only trigger new physics that keeps the rule intact. But what if we imagine ignoring that gravitational collapse? Pretend, for the sake of argument, that you could keep adding detail without triggering a black hole. What would the world look like? At first glance, you might expect a system with infinite precision, infinite resolution, infinite detail. But closer analysis shows contradictions. If information density exceeded the bound, you would be able to encode distinctions smaller than the Planck scale, smaller than any measurable length or time. That would mean physics could not be discrete. It would mean the very idea of measurement would fail, because you would be claiming to resolve more than space-time can support. The theory of quantum mechanics, which limits how much information you can extract from a system, would collapse under the weight of those impossible distinctions. In practice, that tells us that the bound is not just a limit on storage, it is a limit on reality itself. To break it would be to invent a different kind of physics, one where space and time are not emergent from information but something else entirely. Whether such a universe could exist at all is unclear. The bound is stitched into the fabric of the theories we have, and removing it leaves only contradictions. Still, there are fascinating thought experiments that try to push against it. Consider quantum computers. They rely on qubits, which can exist in superpositions, carrying more information than classical bits. Could a quantum computer circumvent the bound by storing exponential amounts of data in entangled states? The answer, as far as we know, is no. Entanglement still obeys the holographic principle. The correlations are rich, but they do not exceed the surface area available. The bound applies even there. The tangle is intricate, but the ceiling remains. Another case comes from cosmology. What if the universe itself were infinite in extent, with infinite regions to hold infinite information? On the larger scales, perhaps infinity could sneak back in. But within any horizon, within any causally connected patch, the bound still applies. You can never exceed the area's informational limit. Infinity, if it exists, is always out of reach, always beyond the boundary of what can be accessed. That means the bound remains unbroken, not by collapse this time, but by horizon. The system enforces itself through limits on what can be observed. Breaking the bound might also be linked to paradoxes of time. If you could encode infinite information in a finite space, then you could, in principle, build a machine that predicts every outcome of every process without error. You could foresee the exact trajectory of every particle, the precise unfolding of the future. Determinism would be absolute and uncertainty would vanish. But uncertainty is fundamental in quantum mechanics. The fact that we cannot know everything is not a flaw of our tools. It is a law of physics. Breaking the bound would mean erasing uncertainty, and that would rewrite the rules of causality, probability, and time itself. The consequences would cascade. If uncertainty vanished, entropy would lose its meaning. Without entropy, the arrow of time would dissolve. Without time's arrow, cause and effect would lose their grip. The bound is not just about information. It is about the very structure of reality. To break it is not to cheat the system. It is to erase the system entirely, to unmake the universe into something unrecognizable. This is why most physicists treat the bound as absolute. Not because they have tested it directly in every situation, but because every attempt to break it collapses into paradox or contradiction. The bound is consistent. It harmonizes gravity, thermodynamics, and quantum mechanics. Without it, those pillars would clash, producing infinities where none should exist. The bound is the peacemaker. It ensures that the cosmos remains finite, structured, and consistent. And yet, imagining what would happen if it could be broken is still useful. It forces us to ask why it exists, why the area rather than the volume sets the limit, why surfaces matter more than insides. It forces us to confront the possibility that our intuitions about reality are deeply misleading. We're used to thinking of the world as filled with things, each carrying its own detail. But the bound suggests the opposite. What matters is the boundary, not the contents. If that rule could be violated, our entire picture of reality would invert. Even if we never break the bound, we may learn by approaching it. High-energy particle collisions, such as those studied in accelerators, are ways of testing how information behaves near extreme densities. We never come close to the bound, but the patterns we see hint at how it might operate. The way entropy grows, the way correlations spread, the way energy transforms into new particles. All of these give glimpses of the underlying ledger. By pushing toward the edge, we read the rules more clearly, even if we never cross the line. Some thinkers also speculate about whether advanced civilizations could exploit the bound. If they tried to build computers that pushed against the maximum information density, what would happen? Would their machines collapse into black holes? Would they find ways to distribute their computations across surfaces, encoding data in holographic forms? The speculation is playful, but it has a serious point. The bound is not just a curiosity. It is a ceiling for technology as much as for physics. Every dream of building unlimited machines must face this barrier. There is also a philosophical layer. To ask what happens if the bound is broken is to ask what it means for rules to exist at all. If laws of physics can be violated, are they truly laws or just approximations? The bound seems so fundamental that its violation would not be like breaking a traffic rule but like erasing the road itself. In that sense, the question shifts. It is not what happens if the bound is broken, but whether reality could exist in any form without it. When you think in this way, the answer seems clear. Without the bound, the world would lose coherence. Infinity would return, not as a grand gift, but as a destabilizing force. Equations would diverge, entropy would lose definition, and measurement would lose meaning. The structure that allows stars, galaxies, and life to exist would dissolve. The bound may feel restrictive, but it is also protective. It keeps reality within workable limits, ensures that existence is not lost to the chaos of infinity. This recognition does not end curiosity, it heightens it. If the bound is unbreakable, then understanding its origin becomes one of the most important questions in physics. Why should the universe care about surfaces? Why should the edges of regions hold the key to their informational content? These are the questions that arise once you accept that the bound cannot be broken. They lead into holographic theories, into the idea that reality itself may be a projection from boundaries, that the deepest truths lie not inside but at the edges, and from here, a natural path opens forward. If the bound is absolute, and if it is surfaces that carry the deepest weight, then perhaps what we call limits are not obstacles, but insights into the nature of being. Perhaps they are telling us something profound about reality, that it is not a boundless ocean, but a shaped, finite, and structured whole. And once you see limits this way, the next question becomes philosophical. What do boundaries mean? Not just for physics, but for ideas, for imagination, for the ways we tell stories about the world. There comes a point, after dwelling on the mathematics and physics of limits, where the conversation naturally drifts into philosophy. Numbers and equations can tell us what the ceiling is, how many bits can fit into a given space, how surfaces enforce constraints. But what those limits mean, and how they shape the way we understand reality, belongs to a broader reflection. If everything in the cosmos is bounded, if knowledge itself is capped, then we are pressed to ask, what do limits tell us about existence? Are they barriers to be resisted, or clues that help us see the deeper form of reality? At first, the word limit feels like a negative. It sounds like a wall, a place where progress stops. In daily life, limits often carry frustration. A limit on time, a limit on resources, a limit on strength. To encounter a boundary is to feel the pressure of desire against the edges of possibility. But philosophy encourages us to look again. A limit is not only what blocks, it is also what defines. A painting is bounded by its frame, a melody is bounded by its length, a life is bounded by its duration. Without those limits, there would be no form, no coherence, no meaning. Infinity, for all its allure, lacks shape. Finiteness, though sometimes frustrating, provides structure. In physics, this becomes especially clear. The Bekenstein Bound does not strip the universe of richness. It ensures that the richness is organized, that the cosmos does not collapse into chaos. Without the bound, infinities would break equations, erase meaning, and dissolve predictability. With it, the universe remains stable, knowable in part, mysterious in part. The limit is not an accident. It is the condition that makes reality possible. Philosophically, this opens the door to another thought. Maybe limits are not simply restrictions placed upon existence, but expressions of its nature. To ask whether ideas can overflow, whether imagination can go beyond the limits, is to wrestle with this tension. Human thought is capable of picturing infinity, of describing endlessness, of imagining what cannot exist. In that sense, ideas can overflow. But when those ideas are tested against the fabric of reality, they meet resistance. The overflow is reined back in, funneled into the boundaries of physics. Our imagination is free, but the universe is not obliged to follow. That does not mean the imagination is wasted. Quite the opposite. The ability to overflow is how progress happens. Every breakthrough in science begins as an idea that stretches past what is known. The concept of atoms, of galaxies, of curved space, of entanglement, of black holes. Each of these was once an overflow, a leap of thought beyond what evidence supported. Some of those overflows were tamed into new truths, others dissolved as errors. The process depends on the tension between overflow and limit. Without the overflow, there would be no creativity. Without the limit, there would be no grounding. In this way, philosophy suggests that the dance between ideas and limits is not adversarial. It is symbiotic. Limits are what give ideas their eventual shape, their test of validity, their form. And ideas are what keep limits from being merely cages. They pressure the boundaries, probe them, reveal their contours. The interplay between them is what keeps inquiry alive. There is also a more personal reflection here. Each of us lives within limits. Physical limits of the body, cognitive limits of the brain, temporal limits of lifespan. Yet within those limits, imagination still finds ways to overflow. You can dream beyond your capacity. You can picture lives you will never live, universes you will never see, possibilities that exceed your time. Those overflows may not change the external limits, but they shape the inner life. They remind us that the human spirit is not only defined by what it can do, but by what it can imagine. The Bekenstein Bound cannot measure the worth of a dream. Still, there is something sobering in the recognition that the universe itself seems to hold firm. The bound is not negotiable. You cannot, by will or by imagination, force more bits into a region than its surface allows. You cannot store infinite detail in finite space. You cannot build a system without horizons. That reality grounds us, reminding us that our ideas, however bold, must eventually submit to the contours of physics. The overflow of imagination is beautiful, but the ledger of existence is strict. And yet, rather than diminishing imagination, this makes it more remarkable. The human mind is able to conceive of what it cannot achieve. We can picture infinities, even though we will never touch them. We can imagine universes without limits, even though ours is bounded. This overflow tells us something profound, that consciousness is not merely about surviving within the rules, but about transcending them in thought, even if not in reality. We carry infinity as an idea, even if the cosmos does not carry it as a fact. There is also the question of meaning. If everything is bounded, does that make existence smaller, less significant? Or does it give significance by providing shape? A song that goes on forever loses its melody. A book that never ends loses its story. Perhaps infinity would erase meaning, not deepen it. Limits make moments possible. They create beginnings and endings, rise and fall, climax and resolution. Without limits, there would be no contrast, no rhythm, no experience. The philosophy of limits reminds us that boundaries may not only constrain meaning, they may generate it. Ideas can overflow in another sense as well. They can exceed our ability to manage them. History is full of examples where imagination outpaced wisdom, where new possibilities opened before humanity was ready to use them responsibly. The development of nuclear energy, the rise of artificial intelligence, the expansion of genetic technologies, all are cases where ideas raced past caution, spilling over the limits of what society could handle. Overflow is powerful, but it carries risks. It can destabilize, overwhelm, or backfire. Limits, whether natural or chosen, provide balance. This duality, overflow and limit, echoes through human culture too. Myths, religions, philosophies all wrestle with the tension between boundlessness and finiteness. Some traditions celebrate infinity, picturing eternal heavens or endless cycles. Others emphasize finitude, teaching the importance of mortality, the urgency of brief lives. Perhaps both are necessary. Infinity inspires awe. Finiteness grounds value. The philosophy of limits does not settle for one or the other. It holds both in view, seeing their interplay as the essence of meaning. As you consider this, another layer appears. If information is bounded, and if our imagination is unbounded, then maybe part of the human role is to bridge that gap. We live in a finite cosmos, but we think in infinite terms. That mismatch drives progress, creativity, and wonder. The overflow of thought ensures that the boundaries are never static. They are always probed, tested, challenged. The limits ensure that the overflow never dissolves into chaos. Together, they shape the story of knowledge. Even so, the temptation remains to ask whether some overflow could eventually bend the rules. Could there be ways of storing information that sidestep the bound? Could emergent physics rewrite the limits? Could ideas one day push reality itself beyond its constraints? Most physicists would say no. The bound is woven too deeply into the structure of space, time, and entropy. But philosophers are less certain, because philosophy entertains not only what is, but what might be. Even if the limits are absolute, the overflow of ideas will continue to imagine their undoing. That too has value. And when you take a step back, you see that the very act of asking these questions is already a form of overflow. To think about whether limits can be broken, whether ideas can surpass reality, is to stretch the mind beyond the present. That stretch is part of what makes humanity unique. We do not only live within the bounds, we imagine what lies beyond them. The bound may never break, but the act of wondering keeps the boundary alive in our minds, shaping curiosity, fueling exploration, guiding discovery. From here, the flow of thought turns towards story. If the universe is bounded, and if ideas overflow, then perhaps existence itself can be seen as a kind of narrative, a weaving of information within limits, full of meaning not despite the boundaries but because of them. What we call reality might itself be a story told within the surface of a cosmic horizon, written in finite bits, yet rich enough to give rise to stars, galaxies, and conscious beings who wonder about it all. When you look up at the night sky, what you see first are the stars, pinpricks of light scattered across a dark canvas, some bright, some faint, some clustered, some solitary. They are beautiful in their own right, glowing spheres of nuclear fire burning across unimaginable distances. For centuries, people thought of the universe as a place made of stars and the empty void between them. That was enough to inspire myths, calendars, navigational systems, and the beginnings of astronomy. But as science deepened, we discovered that the stars are only one layer of what the cosmos contains. Beyond them are galaxies, black holes, dark matter, dark energy. And beneath them are particles, fields, quantum fluctuations. The stars are real, but they are not the whole story. The more physics advanced, the more it began to suggest that the universe is not made of things in the way we once thought. Instead of solid objects stacked within space, Reality seems to be woven of information, correlations, and patterns. The Bekenstein Bound, with its insistence that the surface of a region sets the maximum information inside it, reinforces this perspective. The universe is not just matter and energy, it is also data, bits, arrangements of possibilities. It is a ledger of information, constantly being written, shuffled, and reinterpreted. When you look at the stars, you're not just seeing burning gas. You are seeing records of processes, stories encoded in light, stories that travel across billions of years to reach your eyes. That shift changes how we think of existence itself. If the cosmos is, at its root, informational, then it can be understood as narrative. Each configuration of particles is like a sentence. Each galaxy is like a chapter. Each life, each thought, each discovery is like a phrase in a book whose pages are spread across space-time. The bound ensures that the book has finite pages, finite words, finite characters, but within those pages the richness can be immense. Just as a finite novel can hold infinite meaning, a finite universe can hold endless depth. It is not infinity that gives the cosmos its power, but the way limited bits combine to tell stories. Take, for instance, the starlight itself. A photon leaves the surface of a star perhaps 1 billion years ago. Along its path, it carries a story. The temperature of the star, the chemical composition of its surface, the redshift of its journey through expanding space. When it finally enters your eye, that photon completes its narrative, transforming into an impulse in your brain. You perceive it as light, but it is also information, a tale told across distances so vast that human history is younger than its journey. Multiply that by the trillions of photons reaching Earth every second, and you realize that the sky is not just a scattering of points, it is a library. Stories also emerge in the behavior of matter closer to home. Think about a tree. Its rings record years of growth, drought, abundance. Each layer of wood is a memory written in chemistry, telling of seasons long gone. The tree itself is a story of information processing, taking sunlight, water, and minerals, and encoding them into patterns of branches and leaves. When you sit beneath it, you're sitting beneath a structure that embodies narrative, one written not in words but in atoms arranged over time. Even the smaller systems participate in this storytelling. An atom, with its electrons orbiting the nucleus, is not just a thing. It is a pattern of possibilities, an arrangement of quantum states. It tells a story of forces in balance, of stability that allows chemistry to exist. Without those stories at the atomic level, there could be no molecules, no biology, no consciousness to reflect on them. The stories build layer upon layer, from the smallest scales to the largest. This way of thinking brings us back to the bound. If the universe were only matter and energy, limits might seem frustrating. But if the universe is narrative, the bound is what gives the story coherence. Just as no book can contain an infinite number of words, no region can contain infinite information. The limit is what allows the story to be read at all. Without it, meaning would dissolve into endlessness and nothing could be told. The universe's story is possible precisely because of its boundaries. It also suggests something profound about consciousness. Our minds are not just processing signals, they are weaving them into narratives, creating coherence from fragments. When you remember your childhood, you're not retrieving a perfect ledger of events. You're reconstructing a story, filling gaps, shaping meaning. That act mirrors the way the universe itself is structured. Information exists in finite bits, but what matters is the way those bits are arranged into stories. Consciousness is not an exception to the cosmos. It is an extension of its narrative nature. Consider how civilizations have always responded to the stars. Before telescopes, before physics, people looked at the sky and saw stories. Constellations were imagined figures, heroes, creatures, myths. The patterns of light were woven into tales that explain the seasons, the harvest, the meaning of life. Those myths were not scientifically accurate, but they reflected a deep truth, that human beings naturally turn information into narrative. The cosmos gives us data, we answer with stories. Science, in its modern form, is a continuation of that process. Instead of myths of gods and monsters, we tell stories of entropy, quantum fields, and holographic principles. They are still narratives, still attempts to shape the data into meaning. When physicists describe the holographic principle, they are telling a story of reality as projection. When they describe entropy, they are telling a story of disorder as memory. When they describe black holes as surfaces storing information, they are telling a story of boundaries as bookshelves. These are scientific stories, tested against evidence, sharpened by mathematics. But they are still stories, still ways of framing the finite bits into something coherent. The difference is that these stories can predict, explain, and connect with the world in ways myths could not. Yet the underlying drive is the same, to turn a finite universe into a narrative that can be understood. Seeing the universe as story also changes how we think of value. Stars may be vast, but their significance lies not only in their mass or luminosity, it lies in the stories they tell of fusion, of life cycles, of seeding the cosmos with heavy elements. Human beings too may be small on cosmic scales, but our significance lies not in size but in story. Each life is a narrative written in memories, choices, and connections. The bound may limit the bits, but it cannot limit the meaning those bits hold when woven into story. This perspective suggests that meaning is not something added to the universe from outside. It is intrinsic, arising naturally when finite information is arranged into coherent forms. A galaxy is meaningful not just because it contains stars, but because it tells of formation, rotation, and interaction. A black hole is meaningful not just because it bends light, but because it encodes information at its surface. A human life is meaningful not just because it exists, but because it creates and shares stories. To live is to be part of the cosmic narrative, and this leads toward the next step. If the universe is not just stars, not just matter and energy, but stories shaped by information, then reflecting on those stories is part of what it means to exist within it. As the narration slows, as the listener drifts, the awareness of being part of that narrative grows. The cosmos is not distant and cold. It is close and participatory, and you are woven into its story even in this moment, even as you listen, even as the night stretches quietly around you. The flow moves naturally toward reflection. If all of this is story, if boundaries are what make narrative possible, then perhaps the most profound thing we can do is to pause and consider our place in it. Not to solve it, not to exhaust it, but to reflect on it. When the mind lingers on the cosmos, it is easy to feel the immensity first. Distances so vast that light itself takes billions of years to cross them, masses so heavy that even the language of numbers begins to stumble, timescales that stretch beyond the imagination. Against that backdrop you may feel small, a brief flicker in a story too large to follow, and yet, when you step carefully through the ideas, the weight shifts. The universe is not simply a stage of unthinkable dimensions. It is a place shaped by limits, defined by information, structured so that even the smallest part carries meaning, and in that structure there is always room for you. The Bekenstein Bound began as a scientific question, a technical exploration of what information means in the presence of gravity. Jacob Beckenstein wondered how entropy, energy and boundaries fit together. His equations were precise, mathematical, abstract. But what they revealed was something deeply human. They told us that even in the grandest scales there are rules of finiteness. Every surface sets a cap. Every system is shaped by what it cannot exceed. In place of infinity, there is order. In place of boundlessness, there is coherence. That recognition changes how we see not only stars and galaxies, but ourselves. You're made of atoms, yes, but those atoms are stories. Your body is not infinite. It is finite, shaped by boundaries contained within time. Yet those boundaries do not erase meaning. They create it. The finiteness of memory makes each one precious. The finiteness of days makes each one vivid. The finiteness of attention makes each thought matter. Just as the universe itself is held together by its limits, your life is given depth by its edges. Think about the way the night sky has always inspired reflection. For thousands of years, people have looked upward and asked questions. Where did we come from? Why are we here? What is all this? The stars offered no words in reply, but they offered presence, a presence that invited interpretation. Each culture shaped its own answers, its own stories. The cosmos was not silent because it lacked meaning. It was silent because it allowed meaning to emerge through us. Science continues this tradition. The equations and principles, the discoveries and theories, are not cold facts. They are ways of listening to the quiet presence of the universe, ways of shaping it into stories we can carry. Limits, then, are not just scientific curiosities. They are part of the grammar of existence. They are the punctuation marks in the sentences of reality, the pauses and closures that allow meaning to form. Without them, everything would blur together, indistinct, unreadable. With them, the world can be passed, understood, experienced. You are not apart from that grammar. You live within it, shaped by the same rules, participating in the same narrative. As you think about information limits, you might notice how they echo in your own experience. You cannot remember everything. You cannot know everything. Your mind holds only a fraction of what you encounter. But that fraction is enough. You do not need infinite memory to live a meaningful life. You need a finite memory shaped into story, a continuity of moments that feel like yours. The cosmos works in much the same way. It does not need infinite capacity to hold galaxies, to weave histories, to give rise to life. It needs only the limits that structure its story. There is a gentleness in that realization. The weight of infinity can feel overwhelming, like standing at the edge of an endless abyss. But finiteness offers something else, a sense of intimacy. The universe is not an endless ocean that dissolves you. It is a finite, bounded system in which you belong. The same rules that shape galaxies shape you. The same limits that define horizons define your experience. You're not outside the pattern, you're inside it, part of its expression. And when you reflect on that, the night feels different. The stars are no longer just distant suns. They are threads in a story that also includes you. The galaxies are not unreachable others. They're chapters in the same book, written with the same grammar of limits. Even black holes, those mysterious boundaries of no return, are not foreign. They're librarians of information, keepers of stories, echoes of the same rule that shapes your own memory and presence. The quiet edges of knowledge, where science runs into its current boundaries, are places of mystery. They are not failures, they are invitations. The bound reminds us that we cannot know everything, that there will always be horizons we cannot cross. But those horizons do not erase the value of what we do know. They frame it. They make each discovery feel like a step, not toward completion, but toward a richer relationship with reality. The unknown is not an emptiness. It is a contour, a shape that gives direction to curiosity. In your own life, limits perform the same role. You cannot experience every possibility. You cannot live every life. But within the edges of the one you have, richness unfolds. Each boundary shapes the story, gives it coherence. The overflow of imagination stretches you outward, beyond what is possible, but the limits bring you back, ground you, give form to your days. The interplay of overflow and boundary is not just in physics. It is in you, in every choice, every thought, every pause. This reflection does not aim to conclude, because stories like this one do not really end. They linger, like starlight that continues its journey long after the star has burned away. The universe itself is still unfolding, still writing, still shaping new narratives within its limits. And you are part of that unfolding. Each breath, each thought, each listening moment is another thread in the fabric of information, another line in the cosmic story. So as you rest now, in the quiet, you can let that awareness settle. The stars are out there, shining across distances too large to walk, but the information they send is here, in your eyes, in your thoughts. The limits of the universe are vast, but they include you. The edges of knowledge are quiet, but they are places you can approach, gently, with curiosity. You do not need infinity to belong. You belong already, within the finite story the cosmos tells, a story that is more than stars, more than matter, more than energy. It is a story that includes you, here, now, drifting at the edges of knowledge, carrying your own part of the tale. And in that stillness, the narration continues, not with an ending, but with a continuation that can stretch quietly with you, like a background hum, as sleep gathers, as thoughts soften, as the story carries forward into silence. Thank you for joining me tonight, and for letting your thoughts wander across the vastness of the universe. We've moved together from questions of information to the boundaries that hold it, to the quiet recognition that even limits carry meaning. These hours have been a way of drifting step by step through science shaped into story. And through all of it, you've been here, listening, breathing, letting curiosity guide you deeper into calm. If you found this journey soothing, you can always return, always listen again when you need a place to rest your mind. You're welcome to stay connected, to follow along as we keep exploring the cosmos, thought by thought, idea by idea, in this quiet space we share. And for now, you don't need to hold on to the details. You can let them go. The universe will keep them safe. The equations, the boundaries, the stars themselves, they will still be there tomorrow. All you need to do in this moment is to rest. Feel the comfort of knowing you are part of the story, carried gently within it, not apart from it. As the sound fades, you can let the thoughts dissolve into stillness. The night has room for you. The silence has space for you. You can drift here without hurry, without effort, until sleep gathers you in its own quiet rhythm. So let go, breathe slowly and rest well.